In this video, we'll talk about runtime errors and why they can happen. As the name suggests, runtime errors are errors that happen when the program is executing. These types of errors can be difficult to predict when we're writing our program. These errors include divide by zero errors, file not found errors, out of memory errors, and many, many more. Some runtime errors can cause your program to crash. We use exception handling to help us know when runtime errors happen so we can try to recover from them. We'll see examples of runtime errors later in this course when we work with files. We'll also work with exception handling toward the end of the course. In this video, we'll talk about logic errors and why they can happen. Logic errors are errors or bugs in your code that cause your program to run incorrectly. Logic errors are mistakes made by a programmer. Sometimes the mistakes are careless. Other times the mistakes are because the programmers have incomplete or incorrect information. Other times mistakes occur when one programmer modifies another programmer's code to fix or add something, and they introduce an error as they do this. There are many, many causes for logic errors. It doesn't matter what the cause is, though. They need to be corrected. We need to test our code and debug it to find and correct errors. Suppose we have a program that determines if a person can vote in an election, and you must be 18 years old or older to vote. We haven't talked about if statements yet in this class, but they're very intuitive, and I'm sure you'll follow this little piece of code. First, we test to see if the age is greater than 18. If it is, then we execute the code that's inside those curly braces. Do you see the error? It's pretty easy to see it here because the code is isolated, and I told you there was an error. However, in reality, there's much more code typically involved, and this may just be a small part of a much larger program. The problem in this code is that the test condition should be greater than or equal to 18, or greater than 17. Either one will work. As it's written now, 18-year-olds would not be able to vote. We'll talk about testing throughout the course in the context of learning C++ and best practices. Well, that wraps up this section. Next, you can take the section quiz and attempt the challenge exercise and see how you do. I'm sure you'll do great. If you have any questions, please post them to the course forum. Welcome back. So you're ready for the section challenge. Let's go over the challenge. Create a C++ program that asks the user for their favorite number between 1 and 100. Then read this number from the console. Suppose the user enters number 24. You want to display the following to the console. Amazing. That's my favorite number too. That's exactly what we did in our first program. Now here's the little bit of a twist. You also want to display, no really, 24 is my favorite number. Below are two sample runs of the program. So in this case, we're prompting the user. There's our prompt. The user enters 24. And we print out amazing. That's my favorite number too. No really, 24 is my favorite number. And if I run this program again and I type in 75, I'll get 75. So let me run the program for you so you can see what it looks like. Here we go. This is the prompt to the user. Enter your favorite number between 1 and 100. So let's say I typed in a 50 and press enter. Then you're going to display to the user, amazing, that's my favorite number too. No, really, 50 is my favorite number. That's it. That's the challenge. That's it. That's the challenge. Give it a shot and then come back to the next video and we'll work through the solution together. Welcome back. I hope you were able to solve the challenge. Let's go over it together and I'll give you my solution to it. This is a pretty simple challenge, but it's important that you get it because we have to be able to compile, build, link, and run. Obviously, we don't want any compiler errors. We don't want any compiler warnings. So let's start here. What I've done is I've created a challenge solution project based on the template. And here's my main CPP. It's just a simple hello world. So this is the one I'm going to modify. All right, so let me change a little bit of this. I'm going to get rid of that statement right here, and we'll totally start from scratch. Now remember, we need to include the IO stream library. This is how we do input and output. This is how we do our C-ins and our C-outs. So first thing I want to do is I want to prompt the user. I want to say std, 2 colons, and cout. And there's my insertion operator. I'm just going to simply say enter your favorite number between Let's say 1 to 100. And we'll put a colon there and a semicolon on the end. That will prompt the user. Okay. Now we want to be able to read that number from the user. Remember, when we read something, we need to store it somewhere. So we need to store that in a variable. In this case, it's going to be a whole number, so we're going to use an integer. So I'm just going to say int favorite number, just like we did with that first program we wrote. So that's my favorite number. Perfect. Now I can read into that variable. So I can say std from cin. I want to extract, so I'm using the operator going the other way, into favorite number. Okay, so at this point, I've prompted the user. They've typed in a number. I've read that number, and I've stored that number in this favorite number variable right here. The last thing to do is to print out those two statements. So first I'm going to say cout, and I'll say amazing. That's my favorite number 2. And we'll print a new line here so we can go to the next line. We'll say endl, followed by a semicolon. And this is the only difference now between this program and the one that we wrote previously. We want to be able to display the number. Say, no, really, whatever you entered was or is my favorite number. So in this case, let's do that again. We'll do std, and we'll do again cout, and we're going to write to that stream. And I'll say, no, really. And I'll put a comma here followed by a space because we want this to be spaced out nicely. And I'll show you what the problems may be if you don't do that in a second. And at this point, we're going to insert our favorite number right in here. And we'll do another insertion operator. Remember, we can stream all these things together. We can do as many as we want. And we'll say space is my favorite number. And we'll finish it off with a new line. Let's try that. We'll go up to build, run, and build and execute. We got a clean compile and it's running. Enter your favorite number between 1 and 100. Let's say it's 10. Amazing, that's my favorite number 2. No, really, 10 is my favorite number. Perfect, that's exactly what we wanted to solve. Now, the reason that I put in these little spaces here is because let's say I don't put that space in there, and I don't put the space in here. Just like that. And let's run this again now. You can see that the output's not going to look right. So in this case, let's say I typed in 25. And you can see, amazing, that's my favorite number 2. That's fine. But now look, no really, comma 25, no space between 25 and the little I for, and the lowercase I for is my favorite number. So you can see that the output doesn't really look very nice. So all we're doing is just formatting it. We'll talk more about writing to streams and using manipulators so that we can really get more fine-grained control of what we want this to look like. But for now, we could just put spaces right in here. And we'll try that again. Build and run. My favorite number is 10. No, really, 10 is my favorite number. Perfect. So that's it. And that's the solution to this challenge. As I said, it's a pretty simple challenge, but there's a lot of pieces here that come together. In the next few sections, we'll talk about the structure of the C++ program, as well as variables. We'll talk a lot about variables, how we declare them, how we define them, how we initialize them, and how we use them. But you got a taste of it here. In this section of the course, we'll take a look at the basic structure of a simple C++ program. First, we'll look at the basic components of a C++ program. These includes things like keywords, identifiers, operators, punctuation, comments, and syntax. Then we'll discuss the preprocessor directives that C++ uses. These are the statements that begin with the pound sign or the hashtag. And we'll discuss what they do and how they work. We'll then take a look at the main function specifically and functions in general. Then we'll discuss what C++ namespaces are and why we use the standard namespace so often. That's the std word we've used throughout. We'll then learn about the types of comments that C++ supports and why we use comments in our code at all. Finally, we'll talk about basic stream input-output using cin and cout. Let's get started. In this section, we'll talk about keywords, identifiers, punctuation, operators, and syntax in programming languages. Most languages have keywords. Keywords are part of the vocabulary of a programming language. In most languages, the keywords are also reserved. This means that you, the programmer, cannot redefine their meaning, and you can't use them in a way in which they were not intended. C++ has lots of keywords. In a browser, I've opened up a web page for cppreference.com that lists the C++ keywords. Without a frame of reference, it's difficult to know that this is a lot of keywords. There are around 90 keywords in C++. Java has around 50. C has 32. And Python has 33. 90 is a lot of keywords. Now, in general, the more keywords that a language has, the more complex the programming language grammar. However, there are many keywords in C++ that are rarely used. I've been using C++ for a very long time, and there are some keywords in this list that I've never used. There's no need to sit down and memorize all these keywords. We'll use the keywords as we need them, and you'll learn them along the way. Notice that some of the keywords in this list we've already used. For example, we've used int and we've used return. Here's int right here, and here's return right here. We used that in our first program. Also notice that pound include, main, favorite number, standard, endline, cin, and cout are not in this list. That's because they're not keywords. We'll talk about them next. What's important to remember here is that C++ has a set of keywords that it's defined in the language, and these words are reserved. Now let's go to CodeLite and see the reserved words in our first program. So now I'm back in CodeLite, and I'm looking at the same program that we did in the previous section, the one with the favorite number. You can see that I mentioned that main and pound include and favorite number and so forth were not keywords. Same with standard out, cout, cin, and so forth, and endline, all of these. These are not keywords. These are called identifiers. And there's an important distinction between identifiers and keywords. An identifier is something that the programmer names. So these names have been created by programmers to create something that represents something meaningful to them. There are rules about how to name identifiers, and we'll go into all those in a later section. C++ also has operators. It's got a lot of operators. It's got the operators that you're used to, your addition, multiplication, subtraction, division, and so forth. But in this case, we're using some non-standard operators. For example, this guy right here, that little chevron, is the stream insertion operator. We're going to insert whatever's on the right-hand side of it into that stream. In this case, it's an output stream that gets displayed to the console. Same thing with the string extraction operator. This one takes something from the console and stores it into a variable, in this case, favorite number. There's also that double colon right here. That's the scope resolution operator. We'll talk about all of these operators as we go on to section 9 in the course. C++ also has punctuation. Things like semicolons at the end of statements, curlies, open and close quotes, parentheses. It's got all kinds of punctuation. When you put all of these elements together in a program, you end up with something called syntax. Syntax is the syntax of the programming language, the structure and the meaning of what you want the compiler to understand. The compiler is taking your code and translating it to machine code, and it's translating it based on what you told it you wanted to be done. It's not going to guess. This may sound a little intimidating at this point, but it comes pretty quickly with a little bit of practice. Well, that completes this video. In the next video, we'll talk about the C++ preprocessor, and we'll learn more about that preprocessor directive, pound include. In this video, we'll briefly go over the C++ preprocessor and preprocessor directives. What is the C++ preprocessor? The C++ preprocessor is a program that processes your source code before the compiler sees it. The C++ preprocessor first strips all the comments from the source file and replaces each comment with a single space. Then it looks for preprocessor directives and executes them. Preprocessor directives are lines in the source code that begin with a pound or hashtag symbol. As you can see in this slide, there are quite a few preprocessor directives available. The most commonly used preprocessor directive is the include directive. When the preprocessor sees this directive, it replaces the #include line with the file that it's referring to. Then it recursively processes that file as well. So, by the time the compiler sees the source code, all comments are stripped out and all preprocessor directives have been processed and removed. Preprocessor directives are commonly used to conditionally compile code. For example, suppose you only want to compile a portion of your source code if you're on the Windows operating system. In this case, you would use a preprocessor directive to test to see if you are on Windows, and then perhaps include some Windows-specific libraries. If you're not on Windows, then maybe you want to include some Mac OS X libraries, or use the error directive to abort the compile with an error message. Conditional compilation is beyond the scope of this course, but we'll use several preprocessor directives as we move on in the course. One final note that's very important to understand. The C++ preprocessor does not understand C++. Let me say that again. The C++ preprocessor does not understand C++. It simply follows the preprocessor directives and gets the source code ready for the compiler. The compiler is the program that does understand C++. Okay, that wraps up this video. In the next video, we'll talk about comments in C++. In this video, we're going to talk about comments in source code. Now, comments apply to just about every programming language out there. C++ has two kinds of comments, but before we talk about those comments, let's talk about what comments are in general. Comments are programmer-readable explanations in the source code. Explanations, notes, annotations, anything that adds meaning to what the program is doing. One thing that's very important to understand is that the comments never make it to the compiler. In C++, the preprocessor strips out the comments so that the compiler never sees them. It may sound kind of weird, right? We're writing something that the compiler is never going to see. That's the whole point. This is human readable. This is for the next programmer that's coming down the pipe, or for yourself when you have to go back and modify code. You can leave comments in the code explaining what you did and why you did. C++ has two styles of comments. The first one is just a single line comment, and I'll show you what that looks like. It's basically two forward slashes side by side, and then everything after that until the end of the line will be ignored. So this is a comment, and the compiler will never see that comment. That's only for your eyes only, or for the eyes of programmers coming after you. So that's a single line comment. Typically you see these comments done like this, or you may see them, for example, here, right after this variable declaration here for favorite number. We could do something like // this is where my favorite number is stored, or something like that. That's kind of a silly comment, and I'll talk more about using these things wisely. The compiler is never going to see this because the preprocessor will see the comment and strip it out and just replace it with a single space. Okay, so that's one style of comment. That's a single line comment. The other kind of comment is a multi-line comment, and that's a slash, again a forward slash followed by an asterisk, and then an asterisk followed by a forward slash. So everything between those two elements is a comment and will be ignored. So this could be, this one spreads across lines. So this could be a multiple line comment like that. You do anything you like. And again, it's totally free form. You can make it look however you want. You can indent, you could do anything you want here. Everything in here will be ignored. Okay, so now let's talk a little bit more about these comments and what makes sense, what doesn't make sense. The idea behind programming is literate programming. Basically, your code should be self-documenting. Does that mean we don't write comments? Well, no. So you want to be sure that what you write makes sense. In this case, here's my code. Here's my main, and that's the block of code that I've written. This is pretty self-explanatory. I mean, I'll leave this comment in here. I'll fix that typo here. But there's an integer called favorite number. You're outputting to the console, enter a number, you're reading from the console, and you're printing out some stuff. This code doesn't need any commenting. It's very, very clear what it's doing. That's not always the case. Sometimes code is very complicated. It's using some complex algorithms, maybe using some really clever efficiency tweak to make it run faster, but it makes it less obvious what it's doing. Those are good examples of where you should use comments. Don't comment the obvious. For example, right here, you don't want to say return 0. That's silly. I mean, I know I want to return 0. I just said it in the code. So those kinds of comments you really don't want to use. Also, if you're adding A and B, you don't want to put a comment that says, adding A and B. It's pretty obvious from A plus B what you're doing. So you really want to explain more complicated code. You also want to keep the style of the comments consistent. So for example, I have this line comment here, which goes toward the end of the line. Over here, I really don't want to do the other style comment and do something like that. You want to keep your style consistent. Now, the multi-line comments are often seen at the top of files. So I'll do this, and in this case, CodeLight kind of helps me out a little bit, but I'll do that. So many times you'll see code that looks like this. You'll see a bunch of asterisks on top, and then you'll see a bunch of asterisks down here, creating like a little header block. Now notice I've got a beginning comment here and the end of the comment here. Everything in here will be ignored, but in here you'll see stuff like author, and I'll say Frank, dates, things like that. Copyrights, license information, a lot of that is very commonly seen in a multi-line comment at the top of the source file. Another good example of a good comment would be, suppose that inside this function, I'm doing some kind of algorithm and I've tweaked the algorithm. So I could do something like using a modified version of Dijkstra's algorithm, let's say. To improve space efficiency or anything. Something like that. Now the programmer coming after you understands that you're using Dijkstra's algorithm and you've modified it somewhat. Dijkstra's algorithm is a very well understood algorithm. So you've tweaked it somehow to improve space efficiency. Maybe in the body of that algorithm you can comment what exactly you've done. Okay, so that's an example of a good comment. So again, don't comment the obvious. Good commenting doesn't justify bad code, obviously. You don't want to write really bad code and then put a good comment in there saying something silly. One of the dangers with comments is that many times programmers use comments as version control. So up here you'll see something like, let's say 11/11/2017, and you'll see something like Frank fixed bug in something. And then another program will come across and they'll say 11/13/2017, maybe it's Joe, and Joe added function to do something. That's not a good idea. If you want to use versioning, use version control. Use something like Subversion or Git. Don't write your versioning here. The problem with this is some programmers will do it, some programmers won't, and this really won't be reflective of all the changes that actually occurred in the file. Okay, so again, don't do this. This is not a good idea. Use a real version control system. Finally, if you go back and modify code, make sure you look at the comments and modify the comments if necessary. There's nothing worse than a programmer looking at some code and seeing a comment that looks like this, and then you look at the code and it doesn't look anything like Dijkstra's algorithm because another programmer changed it to something else and didn't change the comment. So it's real important that you keep your comments and your code in sync as you go along. Okay, that's pretty much it for comments. In the next video, we'll talk about the main function itself and talk a little bit about what's going on there. In this video, we'll briefly go over the C++ main function. Every C++ program must have exactly one main function somewhere. A C++ program can consist of hundreds of files, but one of those files must contain the main function. Note that the name main must be written in lowercase letters. When a C++ program executes, the main function is called by the operating system, and the code between the curly braces executes. When execution hits the return statement, the program returns the integer value to the operating system. If the return value is 0, then the program terminated successfully. If the return value is not 0, then the operating system can check the value returned and determine what went wrong. There are two versions of main, and they're both valid as per the C++ specification. So far, we've only seen the version on the left, which returns an integer and has nothing between the two parentheses. This version of main expects no information from the operating system in order to run. This is the version that we'll use mostly in this course. The second version of main is the one on the right. In this version, main expects information from the operating system. So suppose that when you execute the program, you need to pass information into the program from the command line. This is very, very common for command line applications. In this case, we tell the compiler that we need two pieces of information. First, we need the number of pieces of information that were passed in. That's argc. We can use any variable name here, but historically we use argc, which stands for argument count. The second piece of information is the actual arguments that we passed in into the program. This is captured by argv, which is the argument vector. The syntax for argv looks a little strange, but it'll make sense as the course progresses. It's basically a bunch of strings, such as program.exe, argument 1, and argument 2 in this example. We'll talk more about strings and vectors as we move forward, but I wanted to show you both versions of the main function in case you're looking at code out there and you see the second version. Both are perfectly valid and both are commonly seen. Note that main must always return an integer. Main happens to be an example of a function. A function is basically a name that we can use to reference a block of code. In this example, main is everything between the curly braces. Functions are very commonly used, and we'll write our own functions as the course progresses. There'll be an entire section of the course devoted to functions. But main is a very special function. As we learn C++, our entire program will be contained inside the main function. And as our programs become more complex, we'll write our own functions and then classes to better modularize and organize our code. In the next video, we'll talk about namespaces and see how we can use them in our first program. In this video, we'll briefly go over using C++ namespaces. C++ namespaces can be a little confusing when you first see them. As our C++ programs become more and more complex, our programs become a combination of our own code, the C++ standard libraries and their code, and libraries from third-party developers and their code. So as you can imagine, sooner or later, we're going to run into the situation where company X names something the same as company Y. When we use that name in our program, the C++ compiler doesn't know which one to use, so we have something called the naming conflict. For example, suppose another library that we're using has defined a name called cout. Well, that's a big problem, right? Because now C++ doesn't know which cout to use. C++ allows developers to use namespaces as containers to group their code entities into a namespace scope. That means that I could create a namespace called Frank, and I could define cout within that namespace. Now, if a programmer wanted to use my version of cout, all they had to do is say Frank : cout. That's it. If they wanted to use the one in the standard library, they would just say standard : cout. It's as simple as that. Namespaces are used to reduce the possibility of naming conflicts. The : operator is called the scope resolution operator. It's used to resolve which name we want to use. However, many programmers find it tedious to type std : all the time when using cin, cout, endline, and so forth. So, C++ provides a few mechanisms to help in that regard. In this sample code, you can see that we're explicitly telling the compiler to use cin, cout, and endline from the C++ standard namespace using std followed by the scope resolution operator. This is how we've written all our code to this point. Now let's take a look at another way we can do this without so much typing. In this case, we can use the using namespace directive followed by the name of the namespace we wish to use. In this case, the standard namespace. Notice that I no longer have to use std followed by the scope resolution operator when I refer to cin, cout, and endline. The compiler now knows which one to use based on the using namespace directive. This is pretty easy to use, and it's the way I'll do it in this course from this point forward, since it reduces code clutter and it's better from a teaching perspective. However, this may not be the best solution for large programs. Using namespace standard not only brings in cin, cout, and endline, it brings in a bunch of other names that are defined in that namespace. So the possibility exists that you may still have a naming conflict. C++ provides another variant of the using namespace directive. Let's take a look at that. In this case, we have a qualified using namespace variant in which we tell the compiler exactly the names I want to use from a specific namespace. In this case, you can see I'm using 3 using directives, each qualified for a specific name in a specific namespace. The advantage of this approach is that we can still use cin, cout, and endline in our code without the namespace and scope resolution operator. And we're not getting any other names from the C++ standard namespace. For the examples in this course, you can use the namespace standard directive from the previous slides with no problem, but keep in mind that it may not be the best practice in larger programs. That wraps up namespaces. In the next video, we'll take a quick look at basic I/O with cin and cout. In this video, we'll look at basic input-output using cin and cout. Cout, cin, carr, and clog are defined in the C++ standard. To use them, you must include I/O stream. C++ uses a stream abstraction to handle I/O on devices like the console and keyboard. Cout is an output stream that defaults to the console or the screen. Carr and clog are also output streams that default to standard error and standard log respectively. And finally, cin is an input stream that defaults to the keyboard. The insertion operator is used with output streams, and the extraction operator is used with input streams. Let's look at how we can use cout and the insertion operator. The insertion operator inserts the value of the operand to its right, in this case the variable data, into the cout output stream. Since cout is by default the console, the value of data will be displayed on the screen. Since we're using stream abstraction, we can chain multiple insertions in the same statement. This makes basic I/O very easy to do. It's important to understand that the insertion operator does not automatically add line breaks to move to the next line on the console. You must do this explicitly, either by using the endline manipulator or by including a new line character, the /n you see in the last example. If you use the endline stream manipulator, it will also flush the stream. This is important to know since if the stream is buffered, it may not get written to the console until it's flushed. We'll talk more about this when we talk about file streams since it's more applicable there. Let's see how the extraction operator works with cin. The extraction operator extracts information from the cin input stream, which defaults to the keyboard, and stores the information into the variable to the right of the extraction operator. The way in which the information is interpreted is based on the type of the variable. So in this case, if data is an integer, then an integer representation will be read from the keyboard. If data is a double, then a real number will be read and stored. If data is a string, a sequence of characters will be read and stored. Extraction operators can also be chained. In the second example, 2 variables, data1 and data2, will be assigned values read from the keyboard based on their type. The characters entered using the keyboard will only be processed when the enter key is pressed. Cin extraction uses white space, that is, spaces, tabs, new lines, as terminating the value being extracted. That's important to understand, so if you put spaces between the things that you type in, the spaces will be ignored. It's possible that the extraction operator could fail. For example, suppose you want to read an integer and the user enters my name Frank. In this case, the operation fails and the data will have an undetermined value. Cin extraction is very easy and useful. However, we'll later learn about other methods we can use with cin that give us more control over the data that's being input. Finally, we can use the same operators to insert and extract data from file streams. This is pretty cool since the syntax is already familiar and the behavior is very similar. We'll work with files later in this course. Now let's head over to the CodeLite IDE and go over some examples in live code. Okay, so now I'm back in the CodeLite IDE and I've got a Section 5 workspace. Within the workspace, I've created a basic I/O project. And this is the main file for that project. Now what we're going to do is we're going to do some basic I/O using cin and cout, and I'll show you some of the nuances so that you really understand what's going on here. First of all, remember on line 4 we've got to include I/O stream, And on line 6, I'm using namespace standard just to make the code a little bit easier to read. Best practice would be to actually include standard scope resolution operator, cout, and so forth, as we talked about in the last lecture. So, first thing we'll talk about is this statement on line 10 right here. Cout, insertion operator, a string hello world, we got another insertion operator, and then we've got the end line manipulator. What this does is it prints hello world to the console and then advances the cursor to the next line. Okay, I'm going to run this, and I'm going to run it by pressing Control F5, which is the same as run here. So when we build and run, you can see it prints out to the screen, hello world, and then it goes to the next line, and this time elapse message prints out after that. Okay, pretty straightforward. If I leave out the end line, and I'll do that really quickly, and I'll run it again, you could see that it prints out hello world. It does not advance to the next line, and then everything just prints out right after that. Okay, so that's pretty straightforward. Let's take a look at a couple of other examples. Look at this example here. I'm going to uncomment this out. First, I'm displaying hello, and then I'm displaying world, and then I'm displaying an end line at the end. Notice that there is no end line after the first hello. So you would expect that these two should run together with no spaces. So we should see hello world all bunched together. So let's try that. And you can see that that's exactly what happens. You can see hello here followed by world with no spaces. It does advance to the end to the next line because we have that end line manipulator here. Okay, so let's do a few more. And as you can see by default, right here when we use the insertion operator with a string, in this case hello, it does not advance to the next line unless we do it specifically and explicitly. So that's what end line does. So here are 4 more output statements. The first one just says cout hello world, just like we've done before, and advances a line. The next one changed the insertion operators. So you could see that I'm putting hello on the output stream, then I'm putting world on the output stream, and you can see there's a space right before that W there, and then I'm printing a new line. So we're getting the same effect as the previous one. Same here. I could say hello world, but here in this case, you can see that I'm using a /n, a \n. This character right here is a new line character. So what happens is you can embed that new line character in the string, and it will advance to the next line. So it's similar to end line. It doesn't flush the buffer, but it still advances to the next line. And then the last line you can see that there's a couple things going on here. You can see that I've got a new line here, a new line here, and a new line here. So you expect this to print out hello, and then go to the new line, and then print out here, then go to the advance to the next line and print out there, and then advance to the next line here. So that's what we expect. We expect the first 3 statements on lines 15 through 17 to print out exactly the same thing. That's the same effect. And the last one to be a little bit different. So let's try this out. And we'll compile and run here. And you can see hello world, hello world, hello world, exactly the same. And then we have hello out there, 1 word per line. And remember, even though that this is all in one string literal here, we still have the /n's in there, which that's how they work. You embed them inside those strings. Okay, so now let's do a little bit with variables. We'll talk a lot about variables in the next section, but I'm going to declare 3 variables right here. And I'll explain that to you real quick. They're really easy. In this case, I'm declaring 3 variables, num1, num2, and num3. Those are the names. Num1 is an integer, and num2 is an integer. And then num3 is a double. That's a floating point number, like 2.5 or 100.7, a real number. We'll use num2 and num3 a little bit later, but right now we're only going to use num1. So I'm going to comment this line, uncomment this line, and you can see what's happening here. I'm prompting the user, enter an integer. Then I'm reading an integer using the extraction operator. I'm extracting an integer from the input stream, and I'm storing it in num1. You can see it's going right in here. And then I'm simply going to output, you entered whatever they typed in. So let me explain how this works. Here's your keyboard. And remember, CN is by default tied to your keyboard. We can redirect it as we wish, but by default, it's the keyboard. Now what happens is characters are read from your keyboard, and they're not read directly by CN. They're stored in a buffer. This is done to make the program more efficient. So if I type in 123 on the keyboard, then what happens is the numbers are read from the buffer. The characters in this case are read from the buffer, and the compiler knows that num1 is an integer. So it's going to read those characters, and it's only going to process what makes sense to be an integer. So in this case, it's going to read the 1 and say, yep. It's going to read the 2. Yep. It's going to read the 3. Yep. Now we're done. So we've got 123. So 123 gets stored into num1, and that will print out here. Okay. Now you need to press enter when you do this on the keyboard. And also, white space is ignored. So if I type in like 10 spaces or tabs or anything that's considered white space, and then I type in 123, then I type in a whole bunch more white space, it'll all be ignored. Okay, so let's take a look at that in action. And I'll just clear this real quick. And let's run this. And it's going to say enter an integer. So I'm going to type in 123, press enter. Remember, I have to press enter. And it says you entered 123. Just what we'd expect. I'll run it one more time. And this time I'm going to type in a bunch of spaces. I'm pressing the space bar. Now I'm pressing tab. Then I'll press 123. And I'll type in some more spaces. Now when I press enter, you can see you still entered 123. All that beginning white space is ignored. And everything after the 3 is considered not an integer. So this is where if you read from cin again, it's going to start right after that 3. Okay. So that gives you an idea of what's going on there. And let me comment that out again, and we'll keep going through some more examples. In this case, we're going to read 2 numbers. We're going to say enter a first integer, and we're going to read that into num1. Enter a second integer, and we're going to read that into num2. And then we're just simply going to say you entered num1 and num2. Remember, in this case here, num1 and num2 right here will be replaced by whatever values the user typed in. Okay, so let's do this. Let's run this one, and you'll see it's exactly what you would expect. And let's see. Oops, I shouldn't have commented these guys out. Let me uncomment them, and let's try that again. So enter a first integer. Let's say we want to type in 100. And I'm going to press enter. Enter a second integer, 200. I'll press enter again. You entered 100 and 200. Again, just what we expected. Now let me show you something that you might not expect. Let me run this one more time. And I'm going to enter 100, followed by a space, followed by 200. And press enter. You can see my output statement worked. It says you entered 100 and 200, but the output looks a little different, right? Well, you can see what's happening. I've entered 2 integers. So what happens is when I read those integers from the standard input, right, via the extraction operator, it's going to grab both of them. It's not going to wait because it's got both of them in there already. So it's not going to wait for me to press enter 2 times because it's got them in there. Let me show you what that looks like so you can better understand it. All right, so let's say that we're here. And we just ran this program and we entered 100, followed by a space, and I'll just use that character there for a space, followed by 200. Okay, so right here, it's waiting for me. What I did was I entered 100 space 200 and I pressed enter. The extraction operator realizes that num1 is an integer, so it's going to try to read an integer from this stream here. It's going to start right here and it's going to say, I got a 1, a 0, and a 0. Boom, I hit a white space. That must mean that my integer is done. So it's going to take 100 and store it right into num1. Okay. Now it's going to output enter another integer. And it's going to try to read that second integer from the input stream. Well, it's already in there, right? So it's going to start right here and it's going to say 2, 0, 0, hit the end. Aha, that's 200. It's not going to wait for me to press enter because there's already data in that buffer. So in this case, the 200 gets put into num2, and this will print out 100 and 200. So your output will be correct, but the way that the prompts are displayed is a little different because it's got data in that buffer already. Same thing with, let me run this one more time, and I'll show you a little bit of a different example. Same thing with space 100, space tab 200, or 200, yeah. And you can see you entered 100 and 200. It's just ignoring all that space. But it's got those two values in that stream. It's just going to process the stream. It doesn't wait for you to press enter twice. Okay, so I'll comment those out, and we can chain the extraction operator just like we can chain the insertion operator. So in this case, you can see that we've got the cin followed by an extraction operator right there, followed by another extraction operator, right? So what I'm doing here is the output statement for the user is a little different. It just says enter two integers separated with a space. So let's say I enter 100, a space, and then 200. Now this guy is going to read two integers from the input stream, and it'll assign 100 here and 200 here. Okay, let's do that. And you can see right here, enter two integers separated with a space. Remember, I could put leading spaces too if I want, but in this case, I'll just say 100 space 200. And it says here, you entered 100 and 200. This is actually a really handy way to get information from the user. When you want them to enter more than one number, enter three numbers separated by spaces. That's really easy for them to do, rather than say, enter number 1, enter number 2, enter number 3, and so forth. Okay, so that's another option you've got. Okay, so I'll comment this out, and now we'll process some doubles. In this case, if you remember, let me scroll up just a little bit. If you remember, num3 was a double, right? So it's a floating point number, a real number. And what I'll do here is I'll just uncomment this out. And the prompt to the user is enter a double right here. And you're going to read the double into num3 from the input stream. Again, here's the input stream. Suppose I typed in 12.5. That's a real number. It realizes that it needs to read a real number from the input stream because num3 was defined up top as a double. So it's going to come here. It's going to read a 1. It's going to get the 2. It's going to see the decimal point. That's valid in a real number. Then it's going to read the 5. Then it's done. And 12.5 will be assigned here and will be displayed down here. Okay, so let's run that. Enter my double. I'll press 12.5 and enter. And it says right there, you entered 12.5, just like we expected. Okay, so let's do this last one, and I'll show you what could go wrong here. There's always something that could go wrong, right? So let me uncomment that. And look at this example here. This one is saying, enter an integer, and you're going to read the integer into num1. And then it's saying, enter a double, and you're going to read the double into num3. Okay, now if we run this and I type in, let's say 10 and 12 space 12.5, that's not a problem at all, right? Because it's going to read the integer and it's going to say 1, 0, I see a space, I'm done. The 10 goes into num1. Then it's going to read a double here, num3. It's going to say 1, 2, decimal point 5, 12.5, perfect. It's going to go in here. The integer is 10, the double is 12.5, and that'll work just fine. Let me run that just so you can see that. And then we'll do one more example, a couple more examples where you can see some of the issues here. So there's my integer, let's say it's 10, and the double is 12.5. And you can see the integer is 10 and the double is 12.5. Okay, but what happens if I enter something like, let's say 10.5? Something like that. Think about this. Logically, you're probably guessing what's going to happen. It's going to read an integer. So it's going to see the 1 and the 0, and it's going to say, yep, that's an integer. When it sees the decimal point, it knows it can't be an integer anymore. So it's just going to take the 10 and store it here. Then you're going to say, read me a double. Well, it's going to start at the decimal point, and it's going to read 0.5. 0.5 is a double, right? So it's going to store 0.5 here. So your output is going to be 10 and 0.5. Maybe not what you expected, but you can see the behavior makes perfect sense. You're telling it what to do. You typed in 10.5. Well, 10's an integer and 0.5 is a double, and I can read those. So let's try that with 10.5, and we'll see what that looks like. So let's enter the integer 10.5. Now remember, there's going to be that 0.5 left in the buffer, so it's not going to ask me, it's going to ask me to enter the double, but it's not going to wait for me to press enter because it's already got data in the buffer. So I press enter, and you can see enter a double, right? It's not waiting for me here. The integer is 10 and the double is 0.5. Now the last example is, let's run this one more time and we'll do something really weird here. We'll just type Frank. Now that's really wonky because you've just told it that you're going to read an integer and a double, and you just gave it a string of characters here. So if I press enter, you can see what's going on here. The integer is 0 and the double is some undefined crazy small number here. Okay. Well, what happens is when it tried to read the integer, it got the F in Frank and it's lost. So the input failed and it goes into a fail state. From that point on, everything that's happening is unreliable. You can see that the integer got 0. It got basically initialized to 0 there. But everything else after that point is completely unreliable. You've got to be really careful. Now, in real world programs, we're not really using cin to read characters. We're using strings. We're reading them into strings, and then we're trying to convert those strings to numbers or whatever else we really need. But they're really, really handy and easy to use, and that's what we're going to do for the vast majority of this course. We're going to use cin and cout so that we can read numbers and we can output numbers or strings or whatever we like. So that finishes off this video. This is basic I/O using cin and cout. You can see it's pretty straightforward. Don't worry about mistakes right now as we're working through these programs. If it says enter an integer, enter the integer. If it says enter a string, enter the string. Don't worry about error handling, that comes later. In this section of the course, we'll learn about variables and constants. It's virtually impossible to write a C++ program without using variables. Variables are a fundamental concept in programming languages. First, we'll learn what variables are and how to declare them so we can use them. There are rules for how we name our variables, and there are also style issues to discuss as we go along. Then we'll go over some of the primitive types in C++, such as integers, floating point numbers, booleans, and characters. We'll also learn how to determine how much storage is allocated to variables by using the size of operator. Then we'll learn about constants, what they are, and what they're used, and why they're so important to keeping our code correct and modifiable. We'll learn how to declare and use constants, understand literals, and constant expressions. This section is very straightforward and easy to understand. However, the concepts you'll learn in this section serve as fundamental building blocks in C++ programming, since nearly every program you write will have variables and constants. Let's get started. In this video, we'll learn what variables are from a conceptual perspective. This will allow you to better understand how to use variables in your programs. I'm assuming in this course that everyone is familiar with the basic architecture of a typical computer system. That is, memory, a CPU, and a bus that allows the movement of data between the CPU and memory. Random access memory, or RAM, is a contiguous block of storage used by the computer to store information. This information can include computer instructions as well as data. RAM can be thought of as having memory cells, where each cell has an associated location. If we had to program using the specific memory locations, it wouldn't be a lot of fun, and we'd likely have a lot of programmer errors. Imagine saying something like, move 21 to memory location 1002. In many very low-level languages, this is sometimes what we do. However, most programming languages allow you to associate a name with a memory location. Let's see the same example using a variable. In this example, you can see that the memory location 1002 has been associated with the name age. In computing, this is called a binding, and we can move 21 to age. This allows us not to have to worry about what exact memory location age is associated with. If we run the program again, age will likely be associated with a different memory address, and that's okay, since we never knew about it in the first place. Our code will still work. Also, thinking of names that make sense to us makes writing and reading programs much easier. That's the basic idea behind names and variables. Of course, since age is a variable, that means that its contents can vary. So if we turn 22 years old, we can change the value of age from 21 to 22. So to recap, a variable is an abstraction for a memory location. We use abstractions all the time in programming to make it easier for us to deal with complexity. Variables allow us to use a meaningful name to represent a value. It's important to understand that variables have two main properties. First is their type. The compiler needs to know what types of values are legal to store in age. In the first code snippet on the left, we tell the compiler to store 21 in age, but we never told the compiler what is valid to store in age. This will produce a compiler error telling us that age hasn't been declared. In the code snippet on the right, we first declare age to be an integer. Now the compiler knows that only integers are allowed to be stored in age. This is called static typing because the compiler is enforcing these rules when the program is compiled rather than when the program is executing. So remember, variables must be declared before you use them in C++. Their value or contents may change as the program executes. In the next video, we'll learn how to declare and initialize variables so they're ready to use in our programs. Let's go there next. In this video, we'll learn how to declare and initialize variables. Then we'll head over to CodeLite and declare and initialize some variables in live code. The syntax for a variable declaration in C++ is very simple. First, you tell the compiler what the type of the variable is. Then you tell the compiler what the name of the variable is. And finally, you terminate the declaration with a semicolon. Later in this section, I'll go over some of the basic C++ types, but here are a few as a preview. Int is an integer or a whole number. A double is a floating point number. And a string is a sequence of characters like you would see in my name Frank. Also notice that we can declare variables of non-C++ built-in types. One of the very powerful features of C++ is object-oriented programming, which allows us to create our own types. So we can create variables that represent an account or a person using the same syntax as we used for integers and doubles. This is great since it makes our program so much more readable. In the next slide, we'll talk about some of the rules that you must follow when you name variables. Remember, in C++, we must declare our variables before we use them. So let's take a look at some of the variable naming rules. The rules for naming C++ variables are very simple. C++ variable names can contain letters, numbers, and underscores. However, the first letter of the name cannot be a number. It can be an underscore or a letter. As discussed previously, C++ keywords are also reserve words, so you can't use those names. You can't use int, you can't use double as your own names. Also, you cannot declare a variable name that's already been declared in the same scope. So if you declared x to be an integer, you can't do that again. Remember, C++ is case sensitive, so the name age in uppercase is considered different from the name age in lowercase. Let's take a look at a few examples. In the left column of the table, you can see some legal C++ variable names. Since C++ is case sensitive, age beginning with an uppercase A is considered a different name from age beginning with a lowercase a. We can begin our variable names with underscores or letters, and we can also have underscores and numbers within the variable name. The right column has some examples of illegal variable names. The first example is lowercase int. This is not allowed since lowercase int is a reserved word in C++. We cannot have special characters like the $sign or mathematical characters like the plus sign. Also notice that variable names cannot have spaces in them. Now let's talk about cout. Cout is a little different. Cout is a legal name because it conforms to the variable naming rules. However, if you include IOStream in your program, then cout is already defined somewhere else. It's defined by the standard library. So it no longer becomes a valid name. Since it's been defined somewhere, you cannot redeclare it yourself. So the rules that the C++ compiler enforces for variable names are pretty simple, as you can see. Now let's take a look at variable naming style and best practices. The most important thing you can do is to be consistent with whatever naming convention you choose to use. There are many style guides and naming conventions out there. In many cases, you'll be working for a company and they have a specific style and naming convention that you have to use. This has nothing to do with the C++ compiler, but it's still very important. For example, Google has a published C++ style guide, as do many other companies. One of the first decisions you make with regard to variable naming is whether you want to use camel case or underscores to separate words. Both styles make the text more readable by avoiding long streams of lowercase letters, which are harder to read. Camel case capitalizes the first letter of every word in your name and doesn't use underscores. The other style is to use underscores to separate words. Either style is fine. The important thing is to be consistent. In this course, I'll use the underscore style. Please use meaningful names. Don't use obscure abbreviations. For example, instead of using the variable name MOE to represent the mass of the Earth, just use the real name, mass of Earth, with underscores or camel case, either way. Sure, it's a little bit more typing, but your program becomes so much more readable and maintainable. Never use variable names before initializing them. Uninitialized variables can cause all kinds of unexpected results in C++. I'll show you an example of this when we head over to the IDE. Finally, it's best practice to declare your variables as close to when you need them as possible. In other words, if your program uses 10 variables, don't declare all 10 of them at the top of the file and then use them later. Instead, declare them right before you use them. There are many, many more programming best practices, and we'll discuss them throughout the course. So now let's talk about initializing variables. Notice the first line of code in this example, int age. This is a variable declaration that's uninitialized. You have no idea what the value of age is. And that's the problem. If you try to display age, or perhaps use it in some calculation, you'll run into problems because it was never initialized, so its value could be anything. Uninitialized variables are a very common source of programming errors. C++ provides 3 ways to initialize variables. All 3 are equivalent, and they're related to the way that C++ has evolved over the years. The first is to use an assignment operator. That's the equal sign. This will assign 21 to age right when it's created, so it will be immediately initialized. The second uses parentheses around the value, in this case 21. This is a constructor-style initialization. We'll talk about constructors when we talk about object-oriented programming. The final initialization statement is the C++11 initialization syntax. This style of initialization is consistent across different types in C++ and has some benefits that we'll discuss later in this course. I encourage you to use this style of initialization. Now, let's head over to CodeLite and see some of these examples in live code. Okay, so now I'm in CodeLite, and let's write a real simple program that calculates the area of a room in square feet. So the idea is we'll ask the user for the length of the room and the width of the room, and then we'll multiply those two together to calculate the square footage of the room, the area of the room. Okay, now obviously we need 2 variables, but before we do that, let me show you one of the issues with uninitialized variables as we talked about in the previous slides. Let's create a real simple variable here called age, just like we did before, and I'm not going to initialize it on purpose, and what I want to do is just output that value to cout. Let's build this. And I'll execute it, and you can see what's printing out here. You can see there's age, I'm outputting age, and that's the value that's in age right now. Not what we expected, for sure. The problem is that we never initialized the variable age, so the value that's in that variable could be anything, and in this case, it is anything. Okay, so let me show you how that works. So let's go back to our conceptual model. Here's our memory. I've got a memory location. Let's say that that's memory location 2000. That could be anything. And age is associated with that location. Now, in there are a series of zeros and ones. That's how we store values in computers. Whatever value happens to be in there is the value that will be displayed on the console. Remember, when I output age, the compiler is going to grab whatever this value is in here and replace it right in there. In this case, we got that really strange, very large number. The idea is we really want to initialize this guy to something, even 0, before we use it. So you can see here, I'm using it before I initialize it. That's not a good idea. Okay, so let me clear this. And if we now initialize this to, let's say, 0 or 21 or whatever we like, I'll use 21 here. Now we'll build and run. you can see now it's printing out 21. Okay, so that gives you an idea. Now also, when we did not initialize it, the compiler did give us a warning. I'll just right click here and compile. Notice the warning that the compiler is giving me down here. It's saying, warning, age is used uninitialized in this function. That's a clue. Don't ignore those warnings. The compiler is telling you, be careful, you're using something that you never initialized. Okay, so that gives you an idea of what's going on with uninitialized variables. All right, so let me erase this and let's write our program. So what we need here is we need to ask the user for the length of the room and the width of the room. We'll grab those two values from cin, then we'll multiply them together and we'll display the square footage of the room. Really, really simple program, but let's get started. So what we'll do is we'll say cout, and remember I don't have to use standard scope resolution operator here because I'm using namespace. So I'll say enter the width of the room, and we'll assume this is in feet. We'll put a semicolon at the end of that line to terminate it. Now we need to read something into a variable, right? So we need to do cin into something. Well, we need to declare that variable. Let's declare it right up here. We could call it width, and it's going to be an integer, let's say. Remember, we've got to say the type, followed by the name of the variable, followed by a semicolon. This is perfectly fine. Width is probably not a great name. Something like room width is better. It provides much more information to whoever's going to come later and modify this code. So now we've got the room width, and I'm going to enter the room width, and I'm going to read it into room width. Right, now we've got our variable. Now you'll notice a couple of things. One is we never initialized room width. In this case, it's probably okay because I'm going to read something into it before I use it, but best practice is let's initialize that. We'll set it to 0. Now we need another variable, right? We need the length of the room. So I'll just cut and paste this to save a little time here. And I'm going to say enter the length of the room. And we're going to read that into another variable called room length. And again, we'll initialize that to 0. In this case, 0 is fine. You could initialize it to anything that makes sense in your application. All right, so now we'll read that one into room length. I'll just change this variable name right here. So look at what's going on here. We've initialized two variables, room width and room length. They're both integers. Again, notice the syntax. The type name is integer, followed by the name of the variable, and in this case, we're initializing it. I'm prompting the user to enter the width of the room, and I'm reading that integer into room width. Then I'm prompting the user to enter the length of the room, and I'm reading that integer into room length. All I have left to do now is just say cout, and I'll say the area of the room is, and we'll do the calculation here right in line. It's going to be room width times room length. And we may as well say square feet. That's it. We'll complete this with an end line. And I'll clean a little bit of this space up just to make it a little bit more readable. That's it. We're returning 0 at the end. Now let's build and run this. We get a clean compile and it says enter the width of the room. Let's say that the width is 10 feet. Enter the length of the room. Let's say it's 5 feet. Always remember, know what to expect. I expect a 50. Press enter. It says the area of the room is 50 square feet. So we get back what we expected. Always think about what you're going to get back before you do this. Otherwise, you may have errors that you didn't think about. We'll press any key to continue. That's it. That's a pretty straightforward solution. You can see how we use variables, how we can initialize variables, how you can read into variables. Now, a best practice would be, rather than declare these two variables up here, what we could do is we could declare them closer to where we're using them. So in this case, this is the first use of room width. So I could modify this by taking this line here, and I'll just cut it, and I'll paste it right in here. And I'll do the same with room length. I'll cut it from here, and I'll paste it right in here. And again, I'll just clean up the code a little bit, get rid of some of this extra white space. Now you can see what's happening. I'm prompting the user, I'm declaring that variable, I'm reading into it. I'm prompting the user for the length, I'm declaring the variable, I'm reading into it. So this is basically what we talked about in the previous slides. You can see this is a really simple example. Try it out, play around with it. There'll be a challenge exercise at the end of this section that's going to extend this a little bit. So that's the end of this video. This shows you how to initialize variables, use the variables. In the next video, we'll talk a little bit about scope and global variables. In our example programs, we've declared our variables within the curly braces of the main function. These variables are called local variables because their scope or visibility is limited to the statements in the main function that follow the declaration of the variable. This is generally what you want to do. However, sometimes you see variables declared outside of any function. These variables are called global variables, and they can be accessed from any part of your program. Unlike local variables, global variables are automatically initialized to 0. We'll talk more about scope and visibility as the course progresses. However, I wanted to introduce you to this concept here, since there's a lot of code out there aimed at beginning C++ programmers that uses global variables in their examples. Global variables have their place, but they also come with some potential problems. Since global variables can be accessed by any part of the program, this means they can potentially be changed from any part of the program. So if you've got a program that's thousands of lines of code, this can make finding errors and debugging more difficult. Let me show you an example of using global variables in case you see code like this out there as you study C++. I'm in the CodeLite IDE, and you can see that I've declared a variable called age, and age is declared right here, and it's within the scope of main. What that means is that this is a local variable. In other words, it's local to this function. So I can use age within this function. So for example here, I'm using age, and the compiler is going to say, okay, which age are we talking about? And it's going to find the age right here. So if I run this, it'll replace age with 18. This is the way we're going to program in this course. However, you may see code out there that looks a little bit different. Let me show you how that works. You may see code out there where this is not declared inside of main. Instead, it's declared outside of main. This makes age a global variable, which means that it can be accessed from anywhere in the program. So now what happens when the compiler sees age here? First, it looks locally to see if it has a declaration of age. In this case, it does not. Then it looks globally to see if age has been declared at the global level. It has. It finds it right here, and now it prints out 18. Okay, so that's an example of a global variable. The concept, again, is pretty straightforward, and it's possible to have both global variables and local variables. So I could do something like this. I could say int age is 16. And notice that now I have two variables named age. I've got one that's local and one that's global. When the compiler sees the use of age in the output statement, first it looks locally. It looks right here, it finds this age, and it's going to use 16 here. It will not use this one. So this one shadows the outer global variable. That's really all there is to global variables. Lots of times you'll see code, as I mentioned, where you won't see this here at all, and everything is global. They're okay for teaching purposes, but it's really not a good practice to start using global variables all over your code. In this video, we'll learn about some of the commonly used C++ primitive data types. These types are also sometimes called fundamental data types because they're implemented directly by the C++ language. The types we'll discuss in this video are the character types, the integer types, which include both signed and unsigned integers, the floating point types, and the Boolean type. It's important to keep in mind that unlike many other programming languages, the size and precision of C++'s primitive data types are largely dependent on the platform that you're working on and the compiler you're using. This means that as a C++ programmer, you need to be aware of your specific machine and understand how much storage is allocated for these types to effectively use them. The C++ include file climits contains information about the size and precision of the data types for your specific compiler. As you know, computers store information using a binary representation which consists of zeros and ones. And these fundamental type sizes are expressed in bits. The more bits allocated to a type, the more unique values that can be represented. Also, the more bits, the more storage that's necessary to represent that type in memory. In this table, you can see how many values can be represented in a given number of bits. The formula used to calculate these values is 2 raised to the number of bits power. So we can store 256 distinct values in 8 bits, 65,536 distinct values in 16 bits, over 4 billion distinct values in 32 bits, and over 18 billion distinct values in 32 bits. Now let's take a look at the specific primitive types one at a time. The C++ character data type is used to represent characters such as the letter A, X, and so forth. The character data type is often implemented as 8 bits, which means it can represent a maximum of 256 characters. This is plenty to represent the alphabets for many spoken languages. However, some spoken languages have thousands of characters, and in many cases, multiple symbols are combined to form single characters. In order to support these languages, C++ supports a wider character type that can be as large as necessary to represent these characters. Unicode is a common standard used to represent multiple character sets for any language. When we work with characters in this course, we'll use the char data type since it easily supports the Latin character set. C++ also supports the integer data types. Integers are used to represent whole numbers. Both signed and unsigned integers are supported. There are many variants of the integer data type. Let's take a look at some of them. The following tables show the C++ integer data types for both signed and unsigned integers. In addition to those shown in the table, it's possible to store both signed and unsigned integers in the character data type. Notice that some of the keywords in this table are bold and others are italicized. Also, typical sizes are included in the table. For example, if you want to declare a signed integer, you don't need to use the signed keyword, since by default integers are signed. Similarly, if you want an integer type that stores very large numbers, you can simply declare the type as long, and you'll get a signed long integer. If you want unsigned integers, that is, integers that are 0 or positive values only, then you're required to use the unsigned keyword. I know this may seem a little confusing with all the optional keywords, but it's not so bad if you just think that by default, all integers are signed. I know what you're thinking. Which ones of these do I use in my application? And the answer is, it depends. If you want an integer variable that stores ages, then you could use an unsigned int or even an int. If you want an integer to represent the number of kilometers between the planets, then you'd probably want to use an unsigned long. For most applications, using int is perfectly acceptable, but you do need to keep in mind the limitations, especially when you perform math on variables and store results in other variables, since the results may not fit into the variable you're saving to. This could cause an overflow. We'll look at a specific example of an overflow in live code at the end of this video. C++ also supports floating point types. These are used to represent non-integer numbers, such as real numbers like 1.2, 0.5, and pi. It's important to understand that computers have finite storage, and many real numbers have an infinite number of digits after the decimal point. Pi is a perfect example of this. In these cases, computers store an approximation of the real number. There's no way the computer can store numbers such as pi precisely. Floating point numbers are represented internally by the computer as signed numbers with a mantissa and an exponent. You may remember your scientific notation from school, 1.234 times 10 to the 7th power. That's the way they're stored internally. This isn't something you need to worry about since it's handled automatically internally, but it's important to know that these are approximations. There are 3 types of floating point numbers: float, double, and long double. Each has varying precision and size depending on the compiler. Note that long double can store very small and very large floating point numbers. The last primitive we'll learn about is the Boolean type. The Boolean data type is used to represent true and false values. In C++, 0 is false and any non-zero value is true. C++ also includes the true and false keywords that are often used with the Boolean type. As you can imagine, Boolean types are used whenever you need to know if something changes state. For example, game over, key pressed, is invincible. These are all good examples of using the Boolean data type, since their values can be either true or false. Great, now let's head over to CodeLight and see some of these primitive types in action. So now I'm in the CodeLight IDE, and I've created a project called Primitive Types that's in the Section 6 workspace. In this C++ file, I'm going to go over some examples of using the primitive types. We'll start with characters, we'll do integers and floating point numbers, and then at the end we'll do booleans. And I'll also show you an example of an overflow so you can see the typical behavior you get with those. I've written the code ahead of time and I've commented out a lot of it, and what I'll do is I'll uncomment and run pieces of it at a time so you can see it build. So the first thing we want to do is take a look at this first example here. This is a good example of using the character data type. My middle initial is a J, so the variable name is called middle initial, and it's of character data type, so it can hold a single character. The way that C++ represents single characters is with single quotes around the J. Do not put double quotes there, that would make it a string and you'll get an error. So what I'm doing here is I'm simply initializing the middle initial variable to J and then displaying it right here in the output statement. So I'll build and run. And I'm just going to click here, remember, so it doesn't ask me my choice all the time, and I just want to build and execute. You can see here it says my middle initial is J, exactly what I expect. Okay, so now let me uncomment the integer types here. The way that you can comment and uncomment lines very easily is just select the lines you're interested in and just press Control/ or Command/ on a Mac, and that will toggle between a comment and non-comment. Okay, so in this case, I've created a variable called exam score, and I'm initializing it to 55. Now, exam score is an unsigned short int. Remember, we have to say unsigned if we want our variables to be unsigned, but I don't have to say int, I can simply say short. So this is the same as saying unsigned short exam score. Okay, so I'm initializing that to 55, and again, I'll build and run. And now you can see my middle initial is still J, and my exam score was 55. Okay? In this case, we've got another number, and I'll uncomment that out. The number of countries represented in my meeting were 65, and I'm initializing it. This is a simple integer. By default, it's going to be signed. And here it's going to say there were 65 countries represented in my meeting. So let me run that again. I'm pressing Control F5 on Windows just to use the shortcut. And you can see here there were 65 countries represented in my meeting. Now in this case, we've got a much larger number. Let me uncomment these two lines out. And so now I've got people in Florida. That's my variable name. This is the state I live in, and there are 20,610,000 people living in Florida. The last I just checked on Google. So I'm defining this as a long. I'm hoping that that fits in the long. It's a pretty big number. I'm pretty sure it does. Let's try that. So I'll press Control F5 again. We'll run it. And you can see there are about 20,610,000 people in Florida. Okay. Now in this case, how about number of people on Earth? I'll uncomment those two lines. And you can see my variable name is people on Earth. And there are about 7,600,000,000 people on Earth. Now, something that's interesting is as these numbers get bigger and bigger and bigger, they're hard to read, and it's really easy to forget zeros and so forth. So the C++14 standard allows you to use those little tick marks right there. You can put them anywhere you want. It really doesn't care. Just to make it easier for you to read, it strips them out and just creates the number. If this doesn't compile on your end, most likely you're not using the C++14 compiler, you're using the C++11 compiler. You could set it to C++14, or you could just get rid of these little tick marks to make it compile. So when I run this, you'll see something interesting happen. I'm pressing Control F5 again. Notice I'm getting an error. The error says error narrowing conversion. It's trying to fit that number into a long, and it doesn't fit. This is one of the benefits that I mentioned about using the list initialization right here with the curly braces. Notice what happens if I did, but actually, you know what? Let me just run this first as a long, which is really what I want, because otherwise it's not going to fit. So now I've got my long, and I'm going to build and run this. And you can see there are about 7 points. You can see the number is correct. Okay. But if I did a regular initialization, like a C-style initialization with an equal sign here, or an assignment statement, something like that, And we'll go back to long because we know it's not going to fit in a long. And I'll build and run again. Look what prints out. There are about negative 98999 people on Earth. That's an example of an overflow. But you also notice that we didn't get an error. That's one of the benefits of using the list initialization. If I use list initialization, it will catch those problems for me at compile time, which is really, really nice. So again, I'll compile here. I'll control F5. Boom, there's the error. I know I've got a problem. I can fix it. So I'll make this a long. Okay, so hopefully that makes sense. Always use that list initialization syntax. It's so much better. In this case, I want the distance to Alpha Centauri. That's pretty far. This is, I believe, in kilometers. Yep, it's in kilometers because that's what my output statement says. I'll uncomment these two lines. And let's run this. And you can see that the distance to Alpha Centauri is, and that's my number, that's correct. Okay, so that's a good example of an overflow. I'll show you another example of an overflow at the end of this source code that may not be as obvious as this. Okay, so here's a couple of examples using floating point types. Remember, these are real numbers. These are numbers with decimal points. So in this case, my car payment is $401.23. I can uncomment this out. Obviously, if I try to store 401.23 into an integer, I've got a problem because the integer would only hold the whole number. So the 0.23 would get truncated off and I could have a problem. Okay. So in this case, let's run this. And now you can see that my car payment here is $401.23. Okay. If I want to store a larger number, I could use a double. In this case, I'm just storing pi. In this case, I'm hard coding pi to be 3.14159. It could be obviously much longer. And in this case, it's a double. And you can see that there's pi 3.14159. I can also store very large and very small numbers using long doubles. So in this case, I'm storing 2.7 times 10 to the 120th power. That's a very large number. And I'm going to store that into this large amount variable, and then I'm going to display it. So let's build and run. And you can see 2.7 times 10 to the 120th power is a very big number. You can see it's actually storing that correctly. The last one we'll look at is the Boolean type. The Boolean type is a true-false value. So in this case, I'll comment that out. You can see I've got a variable called game over. Let me use the correct underscore style here. I've got a variable called game over, and in this case, you could see that I've been working on a project that's using camel case. Muscle memory kicks in. So in this case, I've got a variable called game over, and I'm initializing it to false. And then I'm saying the value of game over is, and you might expect that this would print out false here, but it doesn't print out false. What it does is it prints out 0. Because as far as C++ is concerned, 0 is false. If it was true, it would print out a 1. Now here's an example of an overflow that's not so obvious, and I'll comment that out. Here I have a variable called value1, and I've got another variable called value2. They're both short integers, and I'm assigning 30,000 to this one and 1,000 to this one. Those numbers will fit in those variables. But then I'm going to create another variable called sum, and I've got value1 times value2. Now I know that the product of those, I guess I should have called it product, huh? Let me call it product just to be a little bit more correct here. There we go. So I know that the product of those two numbers does not fit in a short. So let's compile this. And you can see that the sum of 30,000 and 1,000 is some negative number. Obviously, that's an overflow error. Be very careful with these things. Make sure that, those two pieces each will individually fit in the shorts, but the product certainly can't. Okay. But notice the compiler is helping me here. The compiler is saying, warning, you've got potentially a narrowing conversion here. So don't ignore those warnings, as the compilers do a pretty good job about predicting problems that can happen. Okay, so that concludes this video. You can see some simple examples of creating variables, initializing variables, using some of C++'s primitive types. In this video, we'll learn about C++'s size of operator and about the C-limits and C-float include files. C++ has an operator called size of that returns the number of bytes used to represent any type. Size of can also be used to determine the size of compound types like arrays, structures, and objects. We'll learn about compound types in a future section. In order to determine the size of a specific type, we provide the name of the type inside the parentheses. For example, size of int, size of double. This will tell us the size of that type in bytes on the specific machine and compiler that you're running the program on. You can also determine the size of variables using their names. In this case, you can use the same syntax, or you can omit the parentheses since they're optional for variables. The size of operator gets its information from two C++ include files, C-limits and C-float. C-limits provides information about integral types and C-float about floating point types. These include files also provide a bunch of handy defined constants that we can use to determine the precision of our primitive types. For example, int max tells us the maximum value we can store in an int on this specific machine. There are many others, and you can see some in the examples in this slide. Let's head over to the CodeLite IDE and we'll see what some of these values are on my machine. I'm in the CodeLite IDE, and I've written some code that uses the size of operator. Let me walk you through it. First thing we'll see is that we're including IOStream, and we're also including C-limits. Everything I'm using here will use C-limits. You can get the same information in C-float, and I'll leave that as an exercise for you if you like. First thing we'll do is we'll output size of information for types. So in this case, I'm going to output char, followed by size of char in bytes, size of int, size of unsigned int, short, long, and long, long. Now when I run this, I'll get information about how big or how much storage is necessary to represent a character, an integer, and so forth on my specific machine using this specific compiler. Okay, now the rest of the code is commented out, and again, I'll uncomment that as we go through. So what I'll do is, and I've created a project here called size of operator project, and you can run this code on your machine and see what your values look like. So I'll build and run, and you can see the size of information that's come up. A character is 1 byte, an integer is 4 bytes, an unsigned integer is also 4 bytes. That makes sense because the only difference between an int and an unsigned int is that sign bit and how much precision you can store in it. A short integer is 2 bytes, a long integer is 4 bytes, a long integer is 8 bytes, and there you go. Now, I'm running a 32-bit compiler on a 64-bit operating system. If you're running a 64-bit compiler, these numbers will likely be different. All right, so that takes care of the basic size of for the integral types. Let's look at some of the floating point types. So in this case, you can see that I want the size of a float, a size of a double, and a size of the long double. Okay, so what we can do is we can build and run. And you can see now that a float on this particular machine, again, is 4 bytes. A double is 8 bytes, and a long double is 12 bytes. So that's the amount of storage that it takes to represent these specific types on this machine. Okay, so now the C-limits file contains some pretty nice defined constants. And let's use some of them to see what it's like. In this case, I want minimum value. So I want to know what's the minimum value that I can store in a character. What's the minimum value that I can store in an integer, in a short integer, in a long integer, and in a long integer. And you can see the defines are right here, and those will default to some integers. So let's run this now. Again, I'll build and run. And you can see that the minimum value I can store in a character is -128. That makes sense because a character is 1 byte big. In an integer, you can see the number there. In a short, -32768, the long, and the long. Your numbers may look different on your machine depending on a lot of factors. All right, now we can do the maximum values. And it's exactly the same except we're doing char max, int max instead of char min and int min. I'll run this again and I'll press Control F5 to run. And now our maximum values are for characters 127, for short 32767, and for longs, you can see that's a pretty big number. All right, so that's the use of climits and size of with types. We can also use size of with variable names. And I'll show you an example here where what we have here is, here we've got an integer called age, and we're assigning 21 to it. We're not going to use the 21 at all. All we're interested in is the size of that variable. So rather than size of int, here we're saying size of age. This is one syntactic variant. We can also just say size of age without the parentheses. So I'm doing that for an integer called age, and I'm doing the same for a double called wage. So obviously we would expect the double to be much bigger. But again, what I'm doing in here is I'm using the variable name instead of the type here as well. All right, so let's run this one more time. And what we've got now at the bottom here is that the size of using variable names. So age is 4 bytes. And if you recall here, we know that age is an integer, right? And integer up top is 4 bytes, if you recall that statement at the top. So age is 4 bytes. The other syntax variant gives you exactly the same result. And wage is a double, which is 8 bytes. And you can see our doubles here is 8 bytes. You may be wondering, when in the world would I ever use this stuff? Well, it's important, A, to understand what the size and precision of your types are on your system. Later on, when we deal with arrays and other data structures, sometimes it's nice to be able to understand how big something is, how big each section of it is. This is one of the big differences between C++ and other languages like Java and Python. With those languages, you're really far removed from the machine, so you're programming at a much higher level. C++, we're at a lower level, so we've got to deal with this kind of thing. In this video, we'll learn what constants are in C++. Constants are very much like C++ variables. They have names, the rules for naming is the same, they occupy storage, and they're usually typed. This means that when you declare a constant, you usually declare their type just like you do with a variable. There is one type of constant that is not typed, and I'll talk about that at the end of the video. The big difference between variables and constants is that, unlike variables, the value of C++ constants cannot change once they're declared. For example, if I declare age to be a constant integer and assign 21 to it, then the value of age will always remain 21, and I won't be able to change it. If I try to change it, I'll get a compiler error. Why would you need constants in a program? Let's consider a simple application that uses the number of months in a year throughout the code. We could certainly use the number 12 everywhere we need it. However, 12 could mean a lot of things. And if the program is of significant size, it might not be clear to other programmers that 12 means the number of months in a year. So we could create a variable and call it months in a year and assign 12 to it. And now use that name in our code whenever we need to use 12 in that context. That's a much better solution than hard coding 12. But that's a variable, which means that it can be changed, even accidentally. A better solution is to declare months in a year to be a constant integer and assign 12 to it. Now we can use a meaningful name in our code that means 12, and we can't change it even by accident. C++ gives us several ways to create constants. We can use literals, declared constants, constant expressions, enumerated constants, and finally we can use defined constants. We'll learn about constant expressions and enumerated constants later in this course. Let's see what literal constants are first. Literals are the most obvious kind of constant. We can use literals throughout our code, and we often do. They're used to express specific values. We've already seen examples of literals. In this slide, you can see that 12, 1.56, franc, and the character j are examples of literal constants. For example, the floating point literal constant 1.56 always expresses the value 1.56. Literal constants also have types based on a naming convention. You can be explicit with the types of literal constants. For example, for integer literal constants, you can add certain suffixes to the integer literal to specify a different type. For example, the letters U and L specify unsigned and long respectively. These can be either lowercase or uppercase. This slide shows just a few of the combinations. For floating point numbers, you can use the L and F suffixes as shown in this slide. We can also have character literal constants in C++. We haven't used these yet, but they're commonly used within string literals. They consist of the backslash character followed by another character, and they're called escape codes. You can see some examples in this slide. The cout statement will display hello, then tab over and display there. Then it will go to the beginning of the next line and display my friend. And then it will go to the beginning of the next line again. It's very common to see escape codes embedded in string literals and output statements. By far, the most common way of declaring constants in C++ is to use declared constants using the const keyword. The syntax is exactly like that of a variable declaration, with the const keyword at the beginning. You must initialize the declared constant, or the compiler will give you an uninitialized const error message. What happens if you try to change the value of a constant? You guessed it, you can't. The compiler will give you an error letting you know that the constant is read-only and you can't change it. The last way of declaring constants in C++ is by using the preprocessor directive #define. Let's take a look at that. Defined constants were very commonly used in older C and C++ code. These constants are defined using the #define preprocessor directive. I'm showing you defined constants because you may run into them since there is so much C++ legacy code out there. Here you're telling the preprocessor that wherever it sees the word pi, replace it with 3.1415926. Think of this as a blind find replace, as you might do in a word processor. The preprocessor will gladly substitute one for the other. Since the preprocessor doesn't know C++, it can't type check, and this could lead to difficult to find errors. So please don't use defined constants in modern C++ code. In the next video, we'll head over to the CodeLite IDE and see how we can declare and use constants in C++. First, we'll write a program using literal constants, then we'll refactor the code to use declared constants. In this video, we'll apply some of the concepts that we've learned in this section to solve a problem. What we'll do first is we'll solve the problem using literal constants, and then what we'll do is we'll refactor it to use declared constants. And along the way, you'll see how much better it is to use declared constants. Okay, so here's the problem we're going to solve. Frank has a carpet cleaning service that charges $30 per room, and there's a sales tax rate of 6%. All the estimates are valid for 30 days. So our program is really simple. We're going to prompt the user for the number of rooms they would like cleaned, and we're going to provide an estimate. The estimate will look something like this. You can see here starting at line 13. Estimate for carpet cleaning service, number of rooms, 2. That's the number that the user entered. Price per room, $30. Cost, $60. Obviously, that would be $30 per room times 2 rooms. The tax, which would be 6% based on the $60, which would be $3.60. Then the total estimate would be $63.60, and then you print out this estimate is valid for 30 days. Now I'm using dollars, you could use euros, you could use any currency you like. Also, I know that the formatting isn't right. Obviously, $3.60 would be 3.60. Don't worry about that right now. Let's worry about solving this problem and using literal constants and using declared constants. We'll worry about output formatting in a different section, and we'll go over a bunch of different ways to do formatting, including currency formatting based on your locale. All right, so let's think about how we're going to solve this problem. Programmers often use something called pseudocode. Pseudocode is like an English-like or your own natural spoken language-like representation of the algorithm or the steps necessary to solve the problem. In this example, I wrote down some pseudocode. And pseudocode, don't let anybody tell you that there's a right way and a wrong way to do pseudocode. There really isn't. It's not a programming language. This is something that organizes your thoughts and allows you to solve the problem. Remember, if you can't solve the problem in pseudocode, there's no way you're going to solve it in C or in Java or in any other programming language. So in this case, this is my pseudocode. These are the steps that I want to take to solve this problem. The first thing I want to do, and you can see here on line 23, is prompt the user to enter the number of rooms. Great. I want to display the number of rooms to the user, display the price per room. Then I want to display the cost, which is the number of rooms times the price per room. I want to display the tax, which is the number of rooms times the price per room times the tax rate. Then I want to display the total estimate. The total estimate, of course, is the cost plus the tax. And then I want to display at the end, this estimate is valid for 30 days. So what we want to do is we want to mimic this sample output right here. Okay, so let's get started. What we'll do first is we'll do this using literal constants, and then we'll refactor it using declared constants. So the first thing I'm saying is, hello, welcome to Frank's carpet cleaning service. that's my little introduction. Now I need to ask the user, again, look at the pseudocode, ask the user how many rooms they'd like to be cleaned. Okay, so let's do that. We'll say cout, and we'll say how many rooms would you like cleaned? And I'm going to type this along, and if I make typos and errors, that's fine. I'll fix them along the way, and you'll probably make the same kinds of errors, so you'll see how to fix them. Semicolon at the end, and there's a typo right here. So how many rooms would you like cleaned? Now, let's run this. And what I'm doing is I'm pressing Control F5, which is build and run. And you can see here, hello, welcome to Frank's carpet cleaning service. How many rooms would you like cleaned? Perfect. Now I'd like to put a space between the first line and the second line of output. Now there's a couple of ways I can do that. I can come down here and I could just add another end line, and that'll print 2 new lines at the end, which would be fine. I could also just say cout end line here, which prints out a line. Let's run that and I'll show you what that looks like. Now you can see that there's a line between the first line and the second line. And I can also use a character literal constant right here. And in front of the how, I can put a /n, a \n. That's a new line. Now I can get rid of this, and it has the same effect. So what's going to happen here is it's going to print a new line before it prints the how. So if I run this now, you can see I get the same effect. So this is an example of embedding those escape codes, as I mentioned in the PowerPoint slides, into string literals. So now we're here. Next step is to read in the number of rooms from the user. So obviously we need to use the extraction operator with the cin object, but we need to store that somewhere. So let's create an integer. We'll create a variable here, and we'll call it number of rooms. Best practice is to initialize it, so I'm going to initialize it to 0, and cin, and let's get the number of rooms from cin. Okay, so again, let's see where we're at. We've outputted our prompt, and the user has entered the number of rooms. Now we've got all the information that we need to do our calculations. We know that it's $30 per room, and we know that it's a 6% tax rate. That's all I need. So let's create some output statements, and I'm going to close this down here just to create a little bit more room. All right, so let's go here, and we're going to say cout, and let's put a /n here too, because I'd like a space right here. So I'm going to say estimate for carpet cleaning service. We'll create a new line here. Now we want to display the number of rooms to the user. I'll say number of rooms. And I'll put a $sign in here. I'm not too worried about the formatting. I'm just using dollars, so I might as well put the $sign here. And I want to display the number of rooms. Where do I get that? Well, I get that right from here. That variable right there, the user just entered a number and I stored it in there. So that's going to contain whatever they entered. So there's number of rooms and then end line. All right, let's run this. Control F5. And I've got an error that says I forgot to put an L at the end of the end line. There we go. So let's run this again. How many rooms would you like cleaned? Let's say I want 2 rooms cleaned. Estimate for carpet cleaning services, number of rooms 2. I don't want $1 there. I want $1 for prices. So that I'll fix that error. 2 rooms. Perfect. Okay, so now let's start doing some of the calculations. But first we need to print out the price per room. And that's a given. That was given to us as $30. So we'll say price per room. Here we'll put a $sign. And we'll say 30. We'll use a literal right in there. And we'll say end line. All right, so that's it. Then we'll say, what's the cost? Well, we'll have to do a calculation. So we'll say cout would be cost. And again, I'll put a $sign in here. And what's the cost going to be? Well, the cost is going to be 30 times the number of rooms, right? $30 per room times the number of rooms. And we'll put a new line at the end. Let's test this out as we go. So let's run it. I want 2 rooms cleaned, so I expect the cost at this point to be $60. So 2 rooms, $30 per room, costs $60. So we're good. All right, so let's continue. And we'll say cout, what's my tax? Or my sales tax is, again, I'll use dollar. And my sales tax is going to be the same calculation, right? 30 times the number of rooms. And I've got an extra quote character right here. Let me get rid of it. 30 times the number of rooms times 0.06, which is the tax rate. End line. I'll save this. Let's run one more time. 2 rooms cleaned, $30. It's $60. 6% of 60 is $3.60. Okay, so we're good. Now we're going to calculate the total estimate, which is going to be the cost plus the tax. But first, I just want to print out a nice little line that separates everything together. That's long enough. And I'll put an end line at the end. All right, so now let's say what the total estimate is, and then we just need to say the estimate is valid for 30 days, and we're done. So cout, we'll say total estimate, and again in dollars is going to be, okay, we need to do the calculation again. So we're going to say 30 times the number of rooms, which gives us the cost, right? And I'm going to put some parens around that because I need to add to that plus 30 times the number of rooms times 0.06, which is my sales tax. So that's my cost plus my sales tax, and a new line at the end. Last thing is, let's say cout, this estimate is valid for however many days, and we said 30. And I'll put a space in front of the D just so we have a little room. Another line here, and I think we're good. Let me clean this up a little bit down here so it all fits a little better. All right, so let's run it, and then we'll go over it real quick. I'm going to save it and run it with Control F5. How many rooms would you like cleaned? 2 rooms. Number of rooms is 2. The price per room is 30. The cost is 60. The tax is 360. So you would expect the total estimate to be 6360, which it is. This estimate is valid for 30 days. Cool. Let's try it again. Let's run it again with 1 room this time. 1 room is $30. The cost is $30. The tax is $1.80. Total estimate $31.80. So it looks good. Don't forget to test with 0. So 0 rooms cleaned, 0 cost, 0 tax, 0 estimate. Great. Don't worry about testing with illegal values. We'll learn how to deal with illegal values later. So for example, expect it to use this in a type 0 or something positive in the number of rooms. They're not going to type in -1 or Joe or Frank or anything like that. As I said, we'll deal with exceptions as the course progresses. So that's it. That's the program. It works. It's pretty easy to understand. It follows our pseudocode. But there's a couple of issues here. First, suppose that I want to increase my cost per room or my price per room to $32.50. What do I do? Well, I could do a search and replace. Right? Let's do that. I'll do a search, find and replace. And I want to look for 30, and I want to replace it with 32.50, and I want to do it everywhere. Replace all. Done. I'll close this up, and let's run it. So I want to do 2 rooms. 2 times 32.50 is 65. That's correct. The tax is $3.90. That's correct. The total estimate is correct. Looks good, right? Except for one little thing. This estimate is valid for 32.5 days. You can see that the 30 was replaced with 32.5. I didn't want to do that. So I need to go back to my code, and let's change that to 30. And now we're okay. This is easy to fix in this example because it's really small. But if you've got thousands of lines of code and you're doing search and replaces like this, it's real possible that that 30 is going to be in different places and it doesn't represent price per room. It represents something else. And you just really messed up your program. You made a lot of changes you didn't intend to change. So hopefully you'll see what I mean. I'm going to undo this 30. And I hope I'm back to where I was. Yep, I'm back to where I was with 30. What I want to do here is I want to use declared constants rather than these literal constants. So let's do that. First, let's just create the variable, and then we'll make it a constant. So we need something for the price per room. So let's create that. Let's say int price per room, and we can initialize it to 30. And then the idea being, instead of using 30 here, we'll use that name price per room. Okay. That's okay, but why an integer? That's really doesn't make too much sense, right? It makes sense with 30, but if I change the price per room to 3250 or some real number like that, a floating point number, this won't work very well. So this really should be a double, and I'm going to change that right there. That gives us a floating point number, and the last thing I want to do is I want to make it const. I don't want that to change in my program. I'll always want it to be 30 while this program's running. Okay, now if I try to change that right here, I'll just show you real quick. Price per room, let's say I want to change that to 100. And I'll just compile over here. I'll get a compiler error that says error, assignment of read-only variable price per room. You just told the compiler that price per room is constant, and here you tried to change it. The compiler is saying, no way, you just told me that this should not be allowed. Okay, so that's one of the benefits of constants, as I mentioned in the lecture. So let me get rid of that. And so that's one of the constants we need. We also need another constant. I'll put a 30.0 in here to be more accurate because it is a real number. I need another one for the sales tax. So I could say const, again, double. And I could say sales tax or sales rate or whatever you want to call it. And in this case, it's 0.06. And then finally, let's create another one for the estimate expiry, which is the 30 days. Const, this case it could be an integer, and we'll just say estimate expiry, and we'll initialize that to 30. And this would be a good place for a comment, days. Okay, so now we've got those three constants. What we can do now is let's go through our code and we'll replace that 30, for example, with price per room. That 006 with sales tax and so forth. This is called refactoring your code. Refactoring means changing your code to make it better without changing behavior. That's real important. Refactoring does not change the behavior of your code. It just makes your code better, more modifiable, easier to read, and so forth. So let's do that. I'm going to use price per room here. I'm just going to copy it. And I'll paste it in here, I'll paste it in here, I'll paste it in here, in here, in here, and not in here because that's my expiry. I'll take sales tax, I'll copy that, and I'll paste it here, as well as over here. And then finally, we'll do the estimate expiry right here. All right, so now let's run this again. And the behavior should not change. I want 2 rooms cleaned. 2 rooms at $30 is $60, $360 sales tax, $63.60 is the total estimate, and it's valid for 30 days. Perfect. As you can see, this code is much more readable now. You can actually see what's going on. And more importantly, if I want to change the price per room to $32.50, I only have to do it in one place right up here. So I can make this $32.50, save it, build and run again. 2 rooms, $32.50, which is $65 now is the cost, $390 tax, $68.90, and it's still valid for 30 days. So you can see the benefits of using declared constants. You can just make changes in one place. You're guaranteed that they're not going to change even if you made a mistake and it was an accident. And it makes your code so much more readable and modifiable. Now, although this code is much better now after refactoring, it still has a few problems. And those problems we're going to address as the course progresses. You hopefully have seen that right about here, we're doing a calculation. And then right here, we're doing the same calculation again. And here, we're doing the same calculation again. And here, we're doing it again. Okay, so that's 4 places that we're doing the same calculation. That's 4 places we could mess up. We really don't want to do that. We want to do that calculation exactly in one place. And what we'll do is when we learn about assignment statements and a little bit more about mathematical expressions, we'll do that there. And then a little bit later in the course, we'll use functions to do that in exactly one place. So if you notice that this isn't quite right, you see a lot of duplication of code, you're absolutely right. And we're going to handle that as we go. All right, so let's get ready for the challenge. This is a pretty simple challenge that's based on one of the problems that we solved in this section. If you recall, we had a problem for Frank's carpet cleaning service where Frank charged so much per room. Well, this is a little bit different. In this case, Frank has two charges, one for small rooms and one for large rooms. So as you can see here, he charges $25 for small rooms and $35 for large rooms. The sales tax rate is still 6%, and estimates are still valid for 30 days. So what you need to do here is prompt the user both for how many small rooms they want cleaned and how many large rooms they want cleaned, and then provide an estimate that looks something like this. Number of small rooms, for example, 3, number of large rooms, 1, price per small room, $25, price per large room, $35, calculate the cost, calculate the tax, and then come up with a total estimate and tell them that the estimate is valid for 30 days. Okay, so hopefully that makes a lot of sense. And here's a sample run that you can see. So here, hello, welcome to Frank's carpet cleaning service. How many small rooms would you like cleaned? Well, let's say I want 3 small rooms cleaned and 1 large room cleaned. And you can see here the estimate is number of small rooms 3, number of large rooms 1. That's what I just typed in. The price per small rooms is $25. The price per large room is $35. And the cost is $110. Now, if you do the math, you can see that 3 times 25 is 75, plus 35 is 110. 6% of that is $6.60. If you add it all together, you get $116.60. And then you display this estimate is valid for 30 days. All right, so give it a shot. Take your time. I'm sure you'll do it just fine. If you want to see the solution, in the next video, I'll present my solution to this problem. Welcome back. I hope you had fun trying to solve the problem. I'm sure you did great. As you noticed in the workspace, I created the challenge, which just created an empty shell for the problem. And I've also got the challenge solution, which has my solution to the problem. Okay, so let's start looking at the code here. We know what we had to solve. So let's look at some of these really simple statements first. And I'll mark this up just so it's easier for you to follow. So in this case, I'm simply outputting welcome. Then I've defined a variable here, which is going to hold small rooms, and I've initialized to 0. That's the best practice. I'm prompting the user, and I'm asking them to put in the number of small rooms they want cleaned. I'm doing exactly the same thing here, except we're doing large rooms. And now we've got to define 2 declared constants, right? We're going to declare 1 is the price for a small room, and 1 is the price for a large room, 25 and 35 respectively. We've got our sales tax declared constant here, and we've got our estimate expiry constant. So far, so good. It's exactly the same as we did before. The only thing is I'm adding the large rooms. Okay, so let me clear this, and I'll scroll up just a little bit, and let's take a look at some of the calculations. Here are some of the output statements, and you can see here I'm outputting the number of small rooms, which is just whatever the user typed in, and the number of large rooms, which is whatever they typed in. The price per small room and the price per large room right here, those are our declared constants, which I'm outputting. And now the cost. The calculation is really simple. It's the cost of the small rooms plus the cost of the large rooms. And we calculate each one by price per small room times the number of small rooms plus, and there's my plus sign. Remember, you can split these across lines so you can line up the insertion operators like that. It makes them nice and easy to read. So in this case, I'm just calculating the cost for the small rooms, and I'm adding the cost of the large rooms to it. Same thing with tax. I'm calculating the cost again, and I'm multiplying the whole thing by sales tax. Notice that I've got those parentheses here because what I want to do is I want to calculate the whole cost and then multiply that by the sales tax. Otherwise, I won't get the correct answer. Got to make sure the whole thing is here. So this becomes all the small costs plus all the large costs. Okay, then finally the total estimate just takes the cost and adds the sales tax to it. That's it. The estimate is valid for 30 days, and there's my program. So you can see that my formatting is probably going to be a little bit different from your formatting, and mine might be a little bit more readable. You may not have split things across lines like I did. It's real good practice to split these across lines. That way you can really see what's going on, and it's much, much easier to follow. Okay, well, I hope you enjoyed the challenge, and I hope you did well. Remember, there's a lot of duplicated code here that we're going to clean up as the course progresses. And this program, we'll actually modify this program a little bit later on when we use functions. Okay, so that's it for the challenge. In this section of the course, we'll learn about our first compound data type. A compound type is a type that's made up of other types. First, we'll learn about arrays, what they are and why we use them. We'll go over the syntax for declaring and initializing arrays, and we'll learn how to access the individual elements of an array. Then we'll talk about multi-dimensional arrays. These can be two-dimensional or three-dimensional arrays, or they can be as many dimensions as you need. They can be very useful for modeling grids, boards, and much more complex data types. Then we'll learn about vectors. Vectors are better than arrays in so many ways, and we'll discuss their advantages. In fact, in modern C++, we rarely use raw arrays. Instead, we use vectors. So why cover arrays at all? I think it's important to understand arrays since there's so much legacy C++ code out there, and conceptually they're easy to understand, and they'll add to your overall knowledge of C++. Okay, so let's get started learning about our first compound data type, arrays. In this video, we'll learn about arrays and their characteristics. We'll also see the typical use case for an array. An array is a compound data type or a structured data type. This means that it's a data type that's made up of other data types. For example, a collection of test scores where each test score is an integer is considered a compound data type made up of integers. We say that this is an array of integers. It's important to understand that all elements of an array must be of the same type, and each element can be accessed directly. We'll see some other array characteristics shortly, but first let's see why we use arrays and why they're so useful. Suppose we need to model my test scores in a class. That's pretty easy. We've already seen how to use variables, and this would be a perfect use of variables. So suppose I have 3 test scores that I need to track, and they're all graded as integers out of 100. I can simply declare 3 variables as integers, give them meaningful names, initialize them to 0 or to whatever values I wish. But what if I need to model more than just a few test scores? Suppose I'm a school administrator, and I need to model the test scores for 100 students so that I could do some statistics on them. Modeling each one of them as its own variable with its own name can quickly get out of control. Now I have to keep track of 100 variable names. You could still do it, but it becomes tedious and error prone. What if I had 10,000 test scores to model? You get the idea. This is a typical use case for an array, and that's when they're really, really useful. Arrays allow you to tell the compiler to give you a collection of as many elements as you want and give the entire collection a single name. So you no longer have to name each individual element. Let's go over some of the characteristics or properties of arrays. Arrays are fixed in size. Once you create an array of a specific size, the size cannot change. So if you create an array of 100 test scores and then you need space for more than that, you'd have to go back to your source code, change the max size, and recompile. The size of the array is fixed. Arrays will not grow or shrink on their own while the program is running. As mentioned earlier, all the elements of an array must be of the same type. So we can have arrays of integers, arrays of doubles, arrays of persons, arrays of accounts, and so forth. Arrays are stored contiguously in memory. So if you tell the compiler that you need an array of 100 integers, the compiler will generate code that allocates exactly 100 integers that are contiguous in memory. That means that the memory will be allocated as one chunk. Array elements are individually accessible, so I can access any test score that I wish. You can do that using the position or index of that array element. So I can tell the compiler to give me the second element in the array or the 1500th element in the array. Be aware that array indexes start at 0. This means that the first element in an array is at position 0, not at position 1. And the last element is at position size -1. You can see an example in the figure on the right. Here we have an array of 10 test scores. The array is named test scores, and it's indexed from 0 to 9. Many programming languages have compound data types like arrays, and the majority of them start their array indexes at 0. I know that most of us start counting at 1. With arrays, you must start at 0. This is a common cause of errors in programs, especially with beginning programmers. It's also important to understand that C++ arrays are not bounds checked. That means that there's no check to make sure that when you access an individual array element that it's between 0 and size minus 1. It's the programmer's responsibility to be sure that you don't go over bounds. If you go over bounds, your program may have strange behavior and you could even crash. Finally, in a few sections, we'll talk about iteration or looping. As you can imagine, looping is used all the time with arrays since we often need to loop through the arrays and process every element. Just like variables, always initialize the arrays or they'll contain unknown values. Arrays are extremely efficient in C++ since they are bare bones raw arrays. Later in this section, we'll talk about C++ vectors, which are super powerful, dynamic, and safer to use than arrays. In the next video, we'll see how to declare arrays. In this video, we'll look at the syntax for declaring and initializing arrays. The syntax for an array declaration is very simple. First, we write the type of each element in the array. This is followed by the name of the array variable. Then we provide square brackets, which is the array indexing operator, and in the square brackets we provide the size that we want the array to be. Remember, this size is fixed, so the compiler must know the size of whatever's in the square brackets at compile time. So this can be a constant literal, it can be a declared constant, or a constant expression. In the first example, we're declaring an array named test scores of 5 integers. The second example declares an array named high scores per level of 10 integers. And the third example declares an array named high temperatures of 365 doubles. Notice that days and years are declared constant so the compiler knows its value. Also note that in all 3 cases the arrays have not been initialized. This means that the contents of the array elements could be anything. Best practice is to always initialize arrays when you declare them. Let's see how we can do that. We can also initialize arrays when we declare them, and it's good practice to do so. The syntax is similar to when we initialize primitive variables. We include an initialization list after the declaration. In this list, we can provide as many initializers as we like, separated by commas. In the first example, test scores is initialized to 100, 95, 99, 97, and 88. The initialization works as you would expect. The test scores array element at index 0 is initialized to 100, the element at index 1 to 95, and so on. In the second example, you see that we declared an array named high scores per level of 10 integers, but we only provided 2 values in the initializer list, 3 and 5. In this case, the first 2 elements of the array are initialized to 3 and 5 respectively, and the remaining 8 array elements will be initialized to 0. In the third example, all of the elements of the array high temperatures are initialized to 0. This is a very handy initializer that's used very often. The final example is a little bit different. In this case, I didn't provide any number for the size of the array inside the square brackets. Instead, I'm letting the compiler determine the size of the array based on the number of elements in the initializer list. This form is also often seen. In this case, another array will be of size 5 integers, and they'll each be initialized from 1 to 5. As you can see, the syntax for declaring and initializing arrays is very straightforward. In the next video, we'll look at the syntax for accessing individual array elements. In this video, we'll look at the syntax for accessing individual array elements. The syntax is probably very much like what you expected. We use the name of the array followed by square brackets with the index of the array element that we want inside the square brackets. This is called array subscripting. For example, test score sub 1 refers to the element at index 1 in the test scores array. In the code example at the bottom, you can see that we've declared the test scores array of 5 integers and initialized those integers. Then we have 5 output statements that each displays one of those array elements. Remember that array subscripting or indexing starts at 0, so the first element of an array is at index 0. We use the same syntax for storing values in array elements. In this example, we're getting input from the user via the console and updating the individual array elements from index 0 to 4. We could then display them as we did in the previous slide. We'll talk about assignment statements in an upcoming section, but here you can see that I'm assigning 90 to the first element of the test scores array. Notice that the syntax is the same. That pretty much covers the basics of arrays, but you might be wondering how all this works behind the scenes. Let's see. In C++, the name of the array represents the location or address in memory of the first element in the array. That is, the element with index 0. When we access an array element using the subscript operator and provide an index in the square brackets, the compiler knows that you want the element that is at that offset from the beginning of the array. So all the compiler has to do is a pretty simple calculation. For example, if you want the element at index 2, all the compiler has to do is go 2 integers away from the beginning of the array, and there it is. Or 2 doubles, or 2 whatevers. The compiler uses the size of operator to determine where the element will be. This is one reason why raw arrays in C++ are so efficient. But remember, there is no bounds checking, so be careful. If you have an array of 5 integers and you ask the compiler for the integer at the 10th index, it will gladly do the calculation and give you whatever happens to be at that location. It's your responsibility to be sure that you're within the bounds of the array. Now let's head over to CodeLite and use what we learned and write some code with arrays. Okay, so now I'm in CodeLite. And I'm in the Section 7 workspace and the Arrays project. And here's my main CPP file. What I've done is I've created some examples where I'm declaring and initializing some arrays. I'm accessing array elements. I'm reading from them, storing values in them, and so forth. And that way we can go through this step by step so you can really understand what's going on. I've also commented a bunch of this out. And what I'll do is I'll uncomment as I go, and we'll build on this little by little. So the first thing we're doing here is I'm creating an array right here named vowels. That's the name of my array, vowels. And you'll notice that right in those square brackets, I'm not providing any information. So what I'm telling the compiler is, hey, you figure out how big this is based on the initializer. Okay? So in this case, I've got 5 characters that I'm initializing this to. So the array will be size 5. So what's going to happen is I'll have an array of 5 characters, and I'm initializing them to A, E, I, O, and U. Right, the name of this array is vowels, so I can treat it as such, and it's indexed from 0 to 4. Remember, there is no 5 here, so don't let that confuse you. Fine, now, in this case, I'm saying the first vowel is, and I'm using an output statement, and I'm grabbing vowel sub 0. Well, that's this guy right there. That's the little a. So I expect this to print out the little a. In this case, I'm using vowel sub 4, which is the little u right here, the lowercase u. All right, so let's run this and see what we get. So what I'm going to do is I'm pressing Control F5 to build and run. And the output is the first vowel is A, and I'll move this over here so you can see. The first vowel is a lowercase a, the last vowel is a lowercase u, exactly what we expect. Okay. Now, what would happen, let me clear this real quick. What would happen if I tried to read from the console and I want to store whatever character I read into vowels sub 5? Recall, there is no vowels sub 5, right? It goes 0, 1, 2, 3, 4. What happens here really depends on a lot of things. Obviously, I'm going to read a character and store it in a location that's not part of the array, so there could be something important there, and I just blew it away. My program will likely crash, depending on what operating system you're on and what you're running. Your crash may look different from mine. So let me run this, and hopefully it'll crash. It may not. You never really know with this. Okay, there's first vowel is little a, second vowel is lowercase u. Now I'm going to read. So I'm going to type in, let's say, capital A. And when I press enter, that's my crash. Hopefully you can see that it says arrays.exe has stopped working. Close program. Depending on, again, what operating system you're working on, it may look different. But in this case, this is a good thing. My program crashed. I'm able to fix it. And obviously what happened here was, and I'll comment this out and I'll leave it commented out so it won't keep crashing. Oops, let me do that again. And I'll write something like, out of bounds. That way when you download in the example, you'll know what's going on. Right? I'll say, don't do this. Or be very careful with that. Okay, so that gives you an idea of what happens. It could be a pretty serious problem, and the real problem is that it may not happen every time. You may clobber some information that's just not even important, but you may clobber some information that's real important. Okay, so let's move on. In this example here, let me uncomment this code and I'll walk you through it. In this example here, I'm doing something very similar. I'm creating an array called high temps, and you can see that the name of the array is right there, high temps. Again, I'm not providing the size of the array because I'm letting the compiler figure it out based on my initializer list. There are 4 initializers, so I was going to create an array of 4 doubles, the first one being 90.1, the second one being 89.8, and so forth. Here I'm saying print out high temps sub 0, right? Remember, this would be 0, 1, 2, and 3. So in this case, this will print out 90.1. Now I'm saying high temp sub 0 is 100.7. So what I just did was I just changed the 90.1 to 100.7. This is an assignment statement. We're going to talk a lot about assignment statements in an upcoming section, but they're really, really straightforward when you see them like this. All it says is move this guy into that guy. Okay, so that's what we're doing, is we're just overriding that 98.1 to 100.7. And then when I display it, it's going to display 100.7 now. Okay, so what I expect here is the first time I output that guy, it's going to give me 90.1. Now I'm going to get 100.7. So let's try this out and see if that's exactly what we get. Let me build and run. The first high temperature is 90.1. The first high temperature is now 100.7. So here you can see some examples of declaring, initializing, and accessing array elements. Now here's another example here, and I'm going to comment this out as well. In this case right here, what I've done is I've asked the compiler again to give me an array of 5 integers and call it test scores. What's happening here is I'm getting an array of 5 integers, just like that. It's called test scores. Again, they're indexed from 0, 1, 2, 3, and 4. However, I never initialized them. So what you have in here is junk or garbage memory. Whatever happens to be in there, whatever bit pattern happens to be in there is still in there. So what this code right here is doing is it's displaying each one of those array elements. It's starting at the element at index 0 and going all the way through the element at index 4. This is what we'll do later on with looping. We can do all this in one statement with looping, and we'll learn how to do that a little bit later. Now, when I do this, I'm expecting junk. I have no idea what's in those cells, so I don't know what's going to print out. So let's try it and see. And you can see the junk right here, 4199136 and so forth. There's a 0 in there. The point is, you cannot rely on those values. You really don't know what's in there. Okay, so what do? Well, we can just put a couple of curly braces there in the initializer. That will initialize everything to 0. So if I run this again, I expect to see all zeros. I do. That's exactly what I want. Always initialize your arrays. Never assume that they've got any value in there until you put the value in yourself. I could also put a hard-coded 0 in there, and I'll have the same effect. But what if I do 100? This piece confuses beginning programmers sometimes. You may think that it's going to put 100 in all of those elements, but that's not the case. Let me run it and you'll see what happens. You see that? It put 100 in the first element and then the rest are zeroed out. That's the behavior. You put in less initializers than you have. So watch now, if I put a 90 here, then what's going to happen is it's going to set this element right here. It's going to set this element right here to 100, this element to 90, and then 0, 0, 0. Okay, so that's the behavior when you provide less than the size of the array as far as initializers are concerned. So again, I'll run this real quick. And what you'll see is 100, 90, 0, 0, 0. Let me clear this screen real quick. In this case, what I'm doing here is I'm reading integers from the console and storing them into those array elements from 0 to 4. So whatever was in here before is going to be removed now. So I'm going to initialize this to 100. Let's just go straight down by 10, 70, and 60. So 100, 90, 80, 70, 60 is how I'm initializing this to. I have a 5 here. I don't really need that 5 there. I could just get rid of it like that. I did it before so you can see how it initializes zeros. So I'll just get rid of that 5 right there. It's still going to create an array of 5 integers and initialize them to 190, 80, 70, and 60. Now what I'm going to do is I'm just going to enter different numbers, and then we'll display those new numbers right here with this code, which is the same code as we used before. Okay, so let's do that real quick. We'll build and run. So there's our original array, 100, 90, 80, 70, 60. So suppose I want to go now 10, 20, 30, 40, and 50. And I print them out. Now you can see that array sub 0 is 10, and the next one is 20, 30, 40, and 50. So you can see that those values are read from the console and stored in the array. The last thing we'll do is, this may give you a little bit of a different effect than you thought. Suppose that I want to output just the name of the array. Now you'll notice test scores right here. I'm not saying test scores sub 0 or test scores sub 1. I'm just saying test scores. Let's run this, and then I'll show you exactly what's going on when we come back. So I'm going to run this. And again, let's just enter those scores again. And notice what happens here. It says, notice what the value of the array name is, and you get some hexadecimal number. That number is actually the memory address or the storage location where the array is located. This is the way that C++ works with arrays. The name of the array is the location of the array. Now that's a strange number to write, so I'll just use 1,000 for it. That way we can make it a little bit easier to explain. So let's take a look at how this works. I've created that array, right? Test scores. And test scores is 5 integers, just like we saw before. Again, indexed 0, 1, 2, 3, and 4. This is called test scores. Now, when I say test scores, what's it going to do? Well, it's going to take the address of that variable. That variable is an address. So let's say that the address is 1,000. And then this address is 1,004, assuming that we have 4-byte integers. And this is 1,008, and this is 1,012, and so forth. What prints out here will be 1,000. And the calculation that C++ is doing that we mentioned in the slides. So for example, when I say test scores sub 1, as I'm saying here, what it's going to do is it's going to take test scores, which is 1,000, and it's going to add 1 integer to it, or in other words, go 1 integer away from it. An integer is 4 bytes. There you go. That's the address. That's the calculation it's doing. This is why when test score sub 5 is referenced, it's going to do the calculation and come up with that number right there, and it's going to try to work with this guy. Well, this guy's not part of the array, right? The array ends here, but there's no real boundaries around the array. It's not like protected or anything. So in this case, something is going to change, and it may be a bad thing. You might crash your program. Okay, so hopefully this example helps you understand a little bit about the syntax of arrays, how to initialize them, how to use them, and a little bit more about how they're laid out in memory and some of the issues that you can have with them. In this video, we'll look at the syntax for multi-dimensional arrays in C++. We'll focus on 2-dimensional arrays, but you can use as many dimensions as are supported by your system. While there's no real limit to the number of dimensions you can have for arrays, be aware that some compilers do place limits on this, though the limits are quite high and you're unlikely to reach them. The syntax for declaring multi-dimensional arrays just involves adding another set of square brackets with the new dimension inside them. In this example, you can see we're declaring a 2-dimensional array named movie rating. This array has 3 rows and 4 columns, which means that the total size of the array is 12 integers. We have not initialized this array, so we should assume that the array elements contain garbage data until initialized. Let's see how we might model real-world data using this 2D array. Suppose we want to collect movie ratings. We have movie reviewers, and each reviews a series of movies with an integer rating from 0 to 5. We have 3 reviewers, and each has to review the same 4 movies. We could choose to model this data by having one array of movie ratings for each reviewer. So we could declare 3 arrays of 4 integers each and solve our problem like that. Another option is to use a 2-dimensional array. The first dimension, or row in our grid, is the reviewer, and there would be 4 columns in the grid, one for each movie. This is similar to the layout of a spreadsheet. In the figure, the reviewer is the first index or row of our array labeled in red, and the movie is the second index or column of our array labeled in green. Now it's pretty easy to go to a specific row and column and get or set that movie rating for that specific reviewer and that specific movie. Accessing the specific movie rating is easy. I can ask the user to enter a movie rating as an integer and store it in movie rating sub1 sub2. Suppose the user enters 5. This would update that specific element in the array. I can also display that element to the console using the same syntax. Initializing multi-dimensional arrays uses the same initializer list syntax that we saw with one-dimensional arrays. In this case, we provide in the initializer list the rows of columns. You could do this in a single line, but it's much more readable if you split it across lines as I've done here. You can see the initializer is providing 3 rows of 4 integers each, which is exactly how we declared the array. While 1- and 2-dimensional arrays are by far the most commonly used arrays in programming, extending the syntax to 3 dimensions and more is just as you would expect. Don't forget that the same characteristics hold for multi-dimensional arrays as for single-dimensional arrays. We'll see multi-dimensional arrays again when we talk about iteration in C++. So that's a look at C++ arrays. If you see them in existing code, you'll understand how they work, what they look like, and their syntax. Remember at the beginning of this section I mentioned that we rarely use C++ arrays in modern C++. Instead, we use vectors. Let's take a quick look at C++ vectors. In this video, we'll learn about C++ vectors. Suppose we want to store test scores for students in a class, but registration hasn't started yet, so I don't know how many students I'll have in class. Also, students drop and add as the semester progresses. How can I model this information using an array as we've seen to this point? Remember, C++ arrays are fixed in size, and I need to specify a size when I declare them. So what are my options? Well, I can always set the fixed size of the array to a size large enough so that it's unlikely I'll have more than that number of students. Many times this option is okay, but you'll probably make it too big and waste space. For example, we may have 30 students in the class, but we allocated 50 students in the array. Not only have I wasted storage space, but now I need to keep track of how many students are actually in the array. And of course, sooner or later, you'll get that one student that exceeds the size of the array. So what do? Well, we can use a dynamic array, such as a vector, to solve some of these problems. A C++ vector is part of the C++ standard template library. This is a library of powerful containers, algorithms, functions, and iterators. This means that we have available to us pre-written, pre-tested, easy-to-use components that we can use to help us solve our problems. We'll go over the main components of the standard template library toward the end of this course. We've talked about C++ being an object-oriented language. Well, when we create a C++ vector, we are creating a C++ object, and we can ask the object to perform operations for us. Vectors can grow and shrink in size at runtime, so it's a perfect choice to model my students. Vectors also provide syntax and semantics similar to arrays, so now that we've learned about arrays, understanding vectors will be pretty easy. In addition to the array-like syntax, we can also use lots of really powerful functions like sort, reverse, erase, find, and more. Vectors also give us the ability to use methods that provide bounds checking if we wish. Let's see how we can declare vectors. There are several ways to declare a vector. The syntax for declaring a vector changes slightly from that of declaring an array because vectors are objects. First, we must include the vector library. Also, the vector type is part of the standard library, so we must either use the namespace or use standard and the scope resolution operator. We can create a vector of any type we want, just like we did with arrays. Here's the syntax for vectors. Don't worry at this point what the differences are. We'll cover this in a future section. Since the vector is an object-oriented template class, we must include the type of the elements of the vector inside the angle brackets. So for example, vowels is a vector or a collection of characters. Test scores is a vector of integers. Both these examples create an empty vector that contains no elements. Let's look at a few other ways to declare vectors. In the first example, we declare vowels to be a vector containing 5 characters. In this case, I'm not providing an initializer list. We'll do that in the next slide. Instead, I'm using a constructor initialization syntax which provides information inside parentheses. This tells the compiler that you want 5 characters. In the second example, we declare a vector named test_scores of 10 integers. Unlike arrays, these 10 integers will be automatically set to 0. I don't have to do that explicitly myself. We can also use initializer lists as we did with arrays to initialize vector elements. In this first example, we declare vowels to be a vector containing 5 characters. In the first example, we declare and initialize the vowels vector to the characters A, E, I, O, U. Note that there are single quotes around the character literals, not double quotes. In the second example, we declare and initialize a vector named test_scores to the integers 100, 98, 89, 85, and 93. In the third example, notice that there are 2 values in the parentheses. The first value, a parameter, is the initial size of the vector, in this case 365. The second value is what you want to initialize all the 365 doubles to. In this case, we're declaring a vector of 365 doubles, and we're initializing all of those doubles to 80.0 degrees Fahrenheit. There are also many other ways to declare vectors. You can declare a vector to be a copy of an array or a copy of another vector. I think you're beginning to see how powerful vectors can be compared to arrays. So let's do a quick recap about vectors. We learned that vectors are an object-oriented container defined in the standard template library. We must include the vector include file to use them, and they belong to the standard namespace. Like arrays, vectors allow you to tell the compiler to give you a collection of as many elements as you want and give the entire collection a single name. Vectors are dynamic in size, which means they can grow and shrink as needed at runtime. Like arrays, vector data is stored contiguously in memory. Vector elements are individually accessible. Vector indexes start at 0 and end at position size -1. If you use the subscript operator, that's the square brackets, to access vector elements, then vectors will provide no bounds checking. This provides the same behavior as arrays. However, vectors provide a rich set of functions that do provide type checking. As a programmer, you can decide what you need to use. Unlike arrays, when you declare a vector, the vector elements will automatically be initialized to 0 unless you specify otherwise. So if you declare a vector of 10 integers, these integers will be initialized to 0. They won't contain garbage. Vectors are very efficient. And finally, we commonly use iteration or looping to process vectors just like we do in arrays. Later in this section, we'll talk about C++ vectors. In the next video, we'll look at how we can access individual vector elements, and we'll also see a few of those useful vector functions I mentioned. In this video, we'll look at the syntax for accessing individual vector elements. The first way to access vector elements is to use the array syntax we've already learned, using the subscript operator. That's the square brackets. We use the name of the vector followed by the square brackets with the index of the vector element we want inside the square brackets. For example, test_scores sub1 refers to the element at index 1 in the test_scores vector. In the code example at the bottom, you can see that the syntax is exactly as it was for arrays. Remember that vector subscripting or indexing is the same as in arrays. It starts at 0, so the first element of an array is at index 0. It's important to understand that when we use the subscript operator with a vector, no bounds checking will be done. You have to do it yourself, as with arrays. Now let's look at another way of accessing vector elements. We can also access vector elements using the @ method. This is the vector syntax. Since when we create a vector, we're really creating an object in object-oriented jargon, then we can ask objects to perform operations. These operations are called methods. The syntax is simple. The object name, in this case the name of the vector, followed by a dot called the dot operator, followed by the name of the operation we want performed. This is the method name. Don't worry about the jargon for now. It will come before you know it, and we'll cover it in depth when we talk about object-oriented programming. The C++ vector has a method or operation called at, A-T. So you can ask the vector to give you an element at a specific position, which you provide inside the parentheses. This style is actually much more intuitive since the name at provides context. So in the example, We've declared and initialized a vector named test scores to the 5 integers 100, 95, 99, 87, and 88. If we want to access a specific element, we use the @ method and provide the element index. You can see that the syntax is very easy to read and understand. Test scores at 0 will refer to the first element in the vector. That's element at position 0. We can also use the same syntax when we want to modify vector elements. In this example, we're reading 5 integers from the console and storing these elements into the test scores vector. The last statement is an assignment statement, as we saw with arrays. We're storing 90 into the first element of the test scores vector. You're probably thinking, okay, that's pretty easy. Vectors are just as easy to use as arrays, but when do they change in size dynamically? The vector has a method called pushback that adds a new element to the end of the vector. Remember, all vector elements must be of the same type, so the element you add must be of the same type as all the other vector elements. In this example, we've created a vector called test scores that contains 3 integers, 100, 95, and 99. If this were an array and we wanted to add another test score, we'd be stuck since arrays are fixed in size. However, with vectors, we can use the pushback method and provide the integer you want to add within the parentheses. You can see that I'm asking the test scores vector to push back 80 and then 90. This will add 80 and then 90 to the end of the vector. Now the vector will contain 5 elements, 100, 95, 99, 80, and 90. How does this work? You don't have to worry about it. That's the beauty of vectors and of the other classes in the standard template library. The vector will take care of allocating or deallocating space, adding new values to that space, and so forth. You can concentrate on solving your problem. Okay, but what happens if you're using @ or some other vector method and you go out of bounds? Let's see. If you go out of bounds and you're using a method that does bounds checking, C++ will throw an exception. That's the jargon used to say that an exceptional condition has been encountered and the program can't continue. An error message is displayed and the program will terminate. This is a good thing. Now you have an error message that tells you what the problem was and you can fix it. The error message in this case is pretty long, but it's telling you exactly what happened. The error message may look different depending on the compiler you have, but the information provided will be the same. In this case, I bolded the important parts of the error message. You can see out of range, vector, range check, and the numbers 5 and 2. When you look back at your code, you'll see the vector has 2 elements and you want an element at index 5. You want your program to terminate or crash during testing so you can fix errors, but you don't want it to crash in production. This is where you can do exception handling. This involves catching these exceptions as the program runs and dealing with them so that the program doesn't crash. Exception handling is a more advanced topic, but I want to cover the basics, so there'll be a section at the end of the course just on exception handling. I hope you can see how much better vectors are than arrays and why you should use vectors in modern C++. Now let's head over to CodeLite and use what we learned and write some code with vectors. So now I'm in CodeLite, and let's do some examples with vectors. I'm in the 7-section workspace under the Vectors project. And here's my main file. Notice that I'm including the vector include file. You must do this in order to use vectors. Also, vectors belong to the standard namespace, so either you use the namespace standard or you'll have to do std, scope resolution operator, everywhere you use vectors. Let's talk about a couple of different ways to create vectors. In this first example here, I can create a vector called vowels, and it's a vector of characters, and that's the syntax. We put the type inside the angle brackets. Okay, so in this case, I've got vowels is a vector of characters, and this is an empty vector. Okay, it's of size 0. There's nothing in there right now. The only way to add things to it is to do something like pushback, which we'll do in a little bit. The second example creates a vector called vowels again. In this case, it's 5 characters long, and each one is initialized to 0. This third example here, which is the one I'm going to use in this example, I'm using an initializer list here, so I'm initializing the vector vowels, which is again is a vector of characters, to the characters A, E, I, O, U, which are my vowels. Again, remember that the character literals have single quotes around them, not double quotes. So at this point, I can simply output vowels sub 0 and vowels sub 4, which I expect to print out A and U respectively. Notice that even though I'm using a vector, I'm using the array syntax, so it's very, very familiar. Also remember that using the subscript notation does not do bounds checking. Okay, so let me run this. So there's my sample run, there's my lowercase a, my lowercase u, just what I expect. Alright, so now let's take a look at another declaration of vector. In this first example here, I'm creating a vector called test scores, which is a vector of integers, and I'm creating a vector of 3 integers in this case. All of them will be initialized to 0. In the second example, I'm creating the test scores vector again. Obviously, I have to comment them out. You can't use the same name twice, that's why I'm doing this. It's a vector of integers, 3 of them. Each one is initialized to 100. And so those are 2 variants for constructing these vector objects. The one I'm going to use is this one right here, where I'm saying test scores, again, is a vector of integers, and I'm initializing them to 100, 98, and 89. So in this case, I'm going to get exactly 3 elements in my vector. My vector will be of size 3. Okay, so let's comment this out here. And in this case, I expect it to display 100, 98, and 89. Again, here I'm using the array syntax. So let me run this. And there you go, 100, 98, 89 using array syntax. Now we can also use vector syntax. So let me uncomment this. And now here you can see I'm saying test scores dot at 0. Test scores at 1, test scores at 2. So in this case, I'm using the at method to give me the value at that specific index. Same idea, except that this is a method and this will be bounds checked, which is very important to understand. Also, after I print out those 3 numbers, I'm saying there are so many scores in the vector. Okay, so what does that mean? Well, notice the size method here. This is a method in the vector class. So I can have my vector name and I can just say something like dot size. It's that simple. And this will return however many items are in the vector right now. Right now I have 3 of them. So I expect this to say there are 3 scores in the vector. Remember, the vector can grow and shrink dynamically. So it's important to be able to ask it, hey, how big are you? And that's what the size method does. So I'll run this one more time. And you can see here my test score is using array syntax 198, 89. Now my test score is using the vector syntax 198, 89. We expect that because the vector hasn't changed. But here it says there are 3 scores in the vector. So here we're asking the vector, hey, how big are you? What's your size? And it's returning a 3. In this example here, what we're going to do is we're going to actually put some information into the vector. We're going to use the vector syntax from this point forward. So here I'm saying enter 3 test scores, and then I'm grabbing 3 integers from the console, and I'm putting the first one at 0, the second one at 1, and the third one at 2. So I'm changing those vector elements. And then I just want to display them out again. So I'll uncomment this. Okay, so let's do that. I'll build and run again. Right now we've got 100, 98, and 89 in there. So let's just say I want 10, 20, and 30. And I want to display them out. And there you go. Updated test scores is 10, 20, and 30. So you can see that we've actually changed the contents of those vector elements. Now let's talk a little bit about the dynamic nature of vectors. This is the part that's really, really cool. I'm going to uncomment this bit out here. And notice the code here. It says enter a test score to add to the vector. Remember, the vector at this point has 3 elements in it. I need to read this into some variable. So I've created a simple variable right here called score to add. It's just an integer. This is not a vector. This is not an array. This is just a plain old integer variable. I'm initializing it to 0. That's the best practice. And I'm reading an integer from the keyboard, from the user, and putting it into score to add. Then what I'm going to do is I'm going to tell the test scores vector to push that integer at the back of the vector. So it's going to add it to the vector. If the vector needs to increase in size, it will. That's nothing we have to do. It handles that automatically. Then I'm going to say enter one more test score. So I'll read another test score from the console, and I'll push that score on. So at this point, when we display, we should have 5 integers now in the vector. I'm going to display them all at 0, 1, 2, 3, and 4. And then I'm going to say, hey, test scores, what's your size? And I expect a 5 here. Okay, so let's try that. All right, so I'm going to enter my test scores again. I'll say 10, 20, and 30. Now, remember, our vector contains 3 integers right now, 10, 20, and 30. So let's enter a test score to add. Let's add 100. And now it's saying, give me one more. Let's put in 105. Maybe I got some extra credit. Now, when I press enter, I should expect to see 5 integers displayed, as well as the size of the vector now being 5. So I'm going to press enter, and that's exactly what I see. The test scores are 10, 20, 30, 100, 105. Then it says there are now 5 scores in the vector. That's pretty cool. Let me show you an example of an exception. Right here, I'm saying this should cause an exception because I'm trying to access test scores at 10. If I tried to do something like this and just used array syntax, like that, no bounds checking will happen. I might just get a crash with no error message or anything. Instead, I'm actually saying at 10. And we could try to put a new line. It's not going to matter much because it's not going to do that because there is no 10th element. Let me run this again and I'll enter those numbers again. Okay, so again, we'll say 10, 20, 30. Let's push in 100 and 105. Now we should get an exception, and there's the exception. You can see the program is still stopping, but there's my exception. Terminate called after throwing an instance of out of range. There's a range checking problem, which is at 10, and this guy is 5 big. So that gives you a really, really good clue as to what's going on. All right, I'm going to comment that out so it won't affect us again. And then the last thing we'll do is I'll show you an example of using a 2-dimensional vector. I'll uncomment all of this out. All right, so here, how do we declare a 2-dimensional vector? Well, a 2-dimensional vector is a vector of vectors. So it's a vector of vectors. And this is how I would declare a vector of vectors. I want to declare a vector that contains within it not ints, not floats, not doubles, but a vector. In this case, a vector of integers. And that's my movie ratings. I can initialize them right here. So going horizontally, that would be the first reviewer, the second reviewer, the third reviewer. And going vertically, this would be the first movie, the second movie, the third movie, and the fourth movie. Now, just like I showed you in the slides with arrays, I can use array syntax. So I could say here the movie ratings for reviewer number 1 using array syntax. And I would expect this to print out 1, 2, 3, 4. That's the first reviewer right up here. And in order to use vector syntax, we just use at, but we use it twice. Give me the rating at 0, that gives me this guy. And then once I have that guy, I can take at 0 for him, or at 1 in the next line, and so forth. So if I run this, I would expect to see 1, 2, 3, 4 both times. So let's run it. And we'll get by this part one more time. And there you go. Here are the movie ratings for reviewer number 1. Array syntax, 1, 2, 3, 4. Here are the movie ratings for reviewer number 2. That should have, sorry, number 1 again. That's right. Using vector syntax, 1, 2, 3, 4. Okay, so that basically covers the fundamentals of vectors, how to use them. There's so much more to vector, and we'll talk about all of that when we talk about the standard template library. But congratulations, you've just now created objects, used object methods, and we're on the way to object-oriented programming. Welcome to the Section 7 challenge. The purpose of this challenge is not to solve a specific problem, but to give you a chance to practice with vectors. We'll declare 2 vectors, and we'll add these vectors to a 2-dimensional vector that we'll declare as well. You'll get a chance to work with the vectors at, pushback, and size methods. And you'll also work with a 2-dimensional vector. Then at the end of this challenge, I'll ask you to modify a vector element and analyze the effect it has. You might be surprised by the result. Please go through the challenge in order and implement each of the directives in the challenge. Let's go over the details of this challenge together. First, I'd like you to declare 2 empty vectors of integers named vector1 and vector2 respectively. Then add 10 and 20 to vector1 dynamically using the pushback method. Display those 2 vector elements using the at method, as well as the size using the size method. Do the same thing for vector2, except we're going to add 100 and 200 this time. Then I want you to declare an empty 2-dimensional vector called vector2d. Remember, a 2-dimensional vector is a vector of vectors. Then I want you to add vector 1 to vector 2D using pushback. Then add vector 2 to vector 2D using pushback as well. Then display the elements in vector 2D using the at method. Now comes the interesting part. I want you to change vector 1's first element using the @0 method. And I want you to change it to 1000. Then I want you to display the elements in the 2D vector again using the at method, just like you did before. And then finally display the elements in vector 1. Take a look at the results and see if it's what you expected, and see what you think happened. That's it. Good luck. Have fun. Once you finish the challenge, extend it any way you wish. Remember, the more you practice, the easier programming becomes. Once you finish the challenge, join me in the next video and we'll go over my solution. Welcome back. I hope you enjoyed working with vectors and learned more about how to use them. You can find my solution in the Section 7 workspace in the Challenge Solution project. Let's go through my solution to this challenge one line at a time. I've inserted the challenge directives in my solution as comments, so it's easier to follow along. So, where do we start? First thing we need to do is we need to include the vector library. If you didn't do that, you probably got some syntax errors about vector not found and probably got a lot of errors. Also, we can use the namespace standard. We don't have to do this, but it makes the code a lot less cluttered and it's easier to display for teaching purposes that way. If you didn't include namespace standard, you might have gotten errors, so you probably did something like standard scope resolution operator vector. So let's do the first directive. It says declare two empty vectors of integers named vector 1 and vector 2 respectively. On lines 42 and 43, that's exactly what I'm doing. You can see vector 1 is a vector of integers and vector 2 is a vector of integers. There is no constructor here with the size. There's no initialization list, so these are going to be empty vectors. The second directive on line 45 says add 10 and 20 to vector 1 dynamically using pushback. That's what I'm doing on lines 47 and 48. Vector 1.pushback10, vector 1.pushback20. These two elements will be added to the back of the vector and the storage will be allocated automatically for them. This is where we can see that the vectors can grow. On line 50, we want to display the elements in vector 1 using the at method, and we also want to display the size of the vector using the size method. So you can see that between lines 52 and 55, that's what I'm doing here. On line 53, I'm simply saying, give me the element at vector 1's 0, and then give me the element at 1. So that will display 10 and 20 because that's what's in there. And then I'm going to say vector 1 contains vector.size will return 2 because there's currently 2 elements in the vector 1. So it should display vector 1 contains 2 elements. Okay, so far pretty easy. Let me scroll up just a little bit. And on line 57, we're doing the same thing with 100 and 200, but to vector 2. So I'm adding 100 and 200 dynamically using pushback on vector 2. Vector 2 was empty, so after this, vector 2 should have 100 and 200 and a size of 2. What we're doing on lines 64 through 67 is the same thing we did with vector 1, except we're doing it with vector 2. We're displaying the results. This should display 100, 200, and vector 2 contains 2 elements. Okay, let me scroll up a little bit more. Now on line 69, the directive says declare an empty two-dimensional vector called vector 2D. And there's a little hint there that says remember that a 2D vector is a vector of vectors. So this is how we would declare this. Vector 2D, that's my object, is a vector of integer vectors, or a vector of integers, however you want to pronounce it. So you get the idea there. So it's a vector that can hold other vectors. Therefore, you have the two-dimensionality. On lines 74 and 75, what we're doing is we're adding an entire vector to the vector 2D with pushback. We can do that, right? Because it's a vector of vectors, so I could certainly add a vector to it. And that's what's happening on lines 77 and 78. On line 77, I'm adding vector 1 to vector 2D using pushback, which means that, remember, vector 2D at this point was empty. So storage will be allocated, vector 1 will be put in there. Doing the same with vector 2. So at this point, we'll have a two-dimensional vector that contains 2 vectors. So on line 80, we're displaying the elements in vector 2D using the at method. So you can see here I'm displaying the element at 0, 0, and then the element at 0, 1, and then the element at 1, 0, and the element at 1, 1. So this should display 10, 20, and 100 200. So this is the interesting part now. I've asked you to change vector 1's first element, right? The element at index 0 to 1,000. And then display the vector again. What did you expect? Some of you might have thought that that first element would have changed, right? Because after all, we did put vector 1 into the 2D vector. And you might be surprised that it didn't. And we'll talk about that in a second. But here, we're displaying vector 1 just to see if it actually did change. So let's run this and we'll walk through the output. So I'm going to build and run. And you can see at the beginning we're saying, okay, vector 1, right, we pushed the 10 and the 20, so that was fine. And then vector 1 contains the 2 elements. That's what we expect. Vector 2, we inserted the 100 and the 200, and vector 2 now contains 2 elements. Vector 2D contains vector 1 and vector 2 within it, right? Again, it's a 2D vector. So the first one was 10, 20. The second one was 100, 200. Pretty cool. But now at this point, what we did was, this is where we're at right now. We just changed vector 1's first element to 1,000. And then we printed out that 2D vector again. But you can see the 2D vector, there's no 1,000 here where the 10 is. That's where you would expect it, right? There isn't. The reason for that is that when you add elements to vectors, you actually make a copy of what you're inserting. So that tells you a little bit about what's going on. A little bit later on in the course, what we'll do is we'll have vectors of references or vectors of pointers. And those are a little bit different because here we can actually change what it's pointing to and it'll be reflected in the vector. But when you're using integers and floats and doubles, remember, we're making copies of what we're putting into the vector. All right, so that completes this solution. I hope you enjoyed the challenge, and I'll see you in the next video. In this section, we'll learn about expressions, statements, and operators in C++. Expressions are the building blocks of statements, and statements are the building blocks of programming in C++. You've already seen variable declaration statements and I/O statements, simple assignment statements, and even the return statement. First, we'll talk about expressions and statements in general and their role in programming. Then we'll learn about block statements or compound statements. This allows us to group multiple statements that belong together into a single unit. The last part of this section is all about the main C++ operators in the context of statements and expressions. We'll first discuss the assignment operator, which is the key element of an assignment statement. Then we'll look at C++'s arithmetic operators. These operators allow us to perform math very easily based on the math rules that we learned in school as kids. We'll then look at the increment and decrement operators. These operators are often used in C++ and can be confusing. I'll walk you through how to use them so it's clear. A common use case in programming is comparing two objects. We often need to know if one object is less than, greater than, or equal to another object, and based on that result, we decide what our next action will be. These are the relational operators. After the relational operators, we'll look at the logical operators. The logical operators allow us to embed complex logic into our program so we can solve difficult problems. If we put together expressions containing relational and logical operators, we can solve extremely complex problems. Then we'll learn about C++'s compound assignment statements. They allow us to perform an operation and assign the result of that operation using a simple syntax. Finally, we'll talk about operator precedence. Precedence determines in what order operators are executed. We've got a lot to cover in this section, so let's get started. In this video, we'll learn about C++ expressions and statements. Let's start with expressions. Expressions are the most basic building blocks in programming. Expressions are defined as follows in the C++ standard: a sequence of operators and operands that specifies a computation. We'll see some examples shortly, but for now you can think of an expression as a sequence of operands and operators that compute a value. That's a pretty simplistic view, but it will serve us well until we learn more advanced C++ features. Let's see some example C++ expressions. Let's start with the literal 34. That's an expression whose value is simply 34. Variables such as favorite number in this example are also expressions, since their value is the value of the variable. We can also have mathematical expressions, such as 1.5 plus 2.8, which will add those two numbers, and 2 times 5, which will multiply 2 and 5. There are many more examples of expressions, since there are many operators in C++ and we can combine them to make any expression we wish. If we wanted to test to see if A was greater than B, where A and B are variables, we can use the greater than sign between the A and the B. This evaluates to a Boolean, a true-false value. Notice the last example. This is an assignment expression. We are assigning B to A. This is also an expression because the value of this expression is what we just assigned. We'll talk more about this in a few videos when we talk about assignment statements in detail. Now let's see what makes a statement different from an expression. A statement is a complete line of code that performs some action. Statements are usually terminated with a semicolon. When you first learn C++, it's a very common error to forget to terminate statements with semicolons. Statements usually contain expressions. As you would expect, C++ has many types of statements. It has expression statements, the null statement, compound statements, and more. We'll discuss specific types of statements in the next several sections of the course. Let's see some example C++ statements. The first statement is the declaration statement, which we've already seen in this course when we declared variables. In this example, we declare x to be of type integer. The second is a simple assignment statement where we assign the literal expression 12 to favorite number. The third example is an expression statement. Note that it's simply an expression with a semicolon at the end. It's a pretty useless statement though, since we add two numbers but don't do anything with the sum. The fourth example is x equals 2 times 5 is an assignment statement. First we multiply 2 and 5 and store the product in x. Notice how expressions are used to make up the statement. The next example is an if statement. If statements give you lots of power to control the flow of your program. We'll discuss if statements in detail. But you can see that we're comparing A and B, and if A is greater than B, then we execute the statement that displays to the console. So here you can see an example of a statement that contains another statement within it and is also made up of expressions. The final statement is simply a semicolon. This is the null statement and performs no actions. You don't often use the null statement, but it can come in handy sometimes. C++ has a rich set of operators that can be used to build up expressions. Most of the C++ operators are binary operators, which means they operate on two operands, for example, the multiplication operator. However, some are unary operators, which means they operate on only one operand. An example of this is the unary minus operator, which simply negates its operand. There's even a ternary operator that operates on three operands. This is the conditional operator. The C++ common operators can be grouped into several categories. Assignment operators are used to modify the value of some object by assigning a new value to it. Arithmetic operators are used to perform mathematical operations on operands. The increment and decrement operators are interesting because part of them work like an assignment and part of them work like arithmetic. They're super useful and very commonly used. Relational operators or comparison operators allow you to compare the values of two objects. These are very useful and include equal to, not equal to, less than, greater than, and so forth. The logical operators are used to test for logical or Boolean conditions. For example, if you want to execute a specific statement only when the temperature is less than freezing and it isn't snowing, these include the logical not, and or operators. There are also several member access operators. We've already seen one of them. Remember the array subscript operator. It allows access to a specific member. There are others that work with objects and pointers, which we'll cover later in this course. Finally, there's the other category. This includes those operators that really don't fit very well into the previous categories. In the next several videos, we'll head over to CodeLight and see some examples of these operators in live code. Nearly all programming languages have the ability to change the value of a variable. In C++, we can change the value stored in a variable using the assignment operator. The assignment operator is a single equal sign. It's important to understand that this does not represent equality. In the code sample on this page, we are not asserting that the left-hand side is equal to the right-hand side, nor are we comparing the left-hand side and the right-hand side. In this case, we're evaluating the value of the expression on the right-hand side and storing that value into the variable represented by the left-hand side. C++ is statically typed. That means that the compiler will be checking to see if it makes sense to store the value from the right-hand side to the left-hand side. If it doesn't make sense, you'll get a compiler error saying exactly that. In order to store a value into the left-hand side must be assignable. It can't be a literal, it can't be a constant. If it is, the compiler will produce an error message. We can assign multiple variables all at once in a single assignment statement. This is possible because the assignment expression evaluates to what was just assigned. So it's easy to chain assignment statements together. Let's head over to the IDE and we'll work with the assignment operator in live code. Okay, so now I'm in the CodeLight IDE. I'm in the Section 8 workspace, and the project is called Assignment Operator. We'll go through some examples of how to use the assignment operator and the effects of the assignment operator in this video. So what I've done here is I've created two variables, num1 and num2. I'm declaring them and initializing them to 10 and 20 respectively. And then I've just got a simple output statement that prints out num1 and num2. Right now, this is not assignment. Right, what you see up here right now, and let me just mark that up. What you see here is not assignment, it's initialization. It's important to understand the difference. Initialization happens when the variable is declared and it gets that value for the very first time. Assignment is when you change a value that already exists in the variable. Okay, so let's try to change one of those values. I'm going to type in here just something really simple like num1 equals 100. You notice I just said num1 equals 100. This is one of the ways that programmers read this. Num1 equals 100, assign 100 to num1, move 100 to num1. You'll hear this sort of jargon, but often you'll hear num1 equals 100. And what we mean there is it's an assignment statement. We're not saying that num1 is actually equivalent to 100. This is an assignment statement. Num1 in this case is 10, remember. So what we're doing is we're moving 100 into that value. Okay, so let's break this down and go through this one step at a time so you really see what's going on here. What we're doing is, again, we have a left-hand side, an assignment operator, and the right-hand side. Right? That's an assignment expression. We put a semicolon in the end. Now it's an assignment statement. In this case, we're evaluating the right-hand side expression. In this case, it's 100. It's a literal. It's going to evaluate to 100. Okay. Now, here is my variable num1. Currently, it has a 10 in there. You can see that right there. I initialized it to 10. When we say something like num1 equals 100, or again, assign 100 to num1, we're evaluating that right-hand side. In this case, as I said, it's 100. And we're storing that 100 into num1. Okay. But num1 is 10. Yes, but when you use num1, this variable num1 on the left-hand side, we're using its location, not its value. In C++, there's the concept of L value and R value. And it gets pretty complicated when we're talking about more advanced features in C++. But at this level, it's really pretty simple. The R value is the contents of some variable, let's say. In this case, the contents of num1 is 10. So the R value of num1 will be 10. The L value is the location of that variable. So again, what this means is move 100 or store 100 into the location of num1. So what's going to happen is that we just changed the 10 to 100. Okay, again, conceptually, it's a pretty straightforward thing. So let me clear this and we'll run it. And what we expect now is we expect num1 to be 100 and num2 to still be 20 because we haven't messed with it at all. Let me compile and run. And you can see num1 is 100 because we've changed it in the assignment statement, and num2 is 20. Okay, it's pretty simple. We don't have to use literals here. We can use anything we like. In this case, I could say num2. Okay, so remember, because this variable num2 is on the right-hand side of that assignment statement, we're using its R value or its contents. We're using the 20 basically. So we're taking the 20 and we're assigning it to the location where num1 is, that box where num1 lives. Okay? So it's going to change that guy to a 20. Okay? Or we'll put a 20 in num1, however you want to look at it. It all means the same thing. So now when we print these two values, we should get 20 and 20. So let's give it a run. So I'm building and running, and now we've got 20 and 20. Remember, we've got a left-hand side, the assignment operator, and the right-hand side. followed by a semicolon. This right-hand side could be really, really complex. I mean, it could be some really, it could be some really complex mathematical expression that just goes on and on and on and on. It doesn't really matter. What the compiler is going to do is going to evaluate this expression to some value. And then it's going to assign that value that was just calculated into that variable. The compiler does type checking for us. Remember, C++ is statically typed, which means that a lot of errors are caught by the compiler. This is very different from other languages like Python and Ruby and so forth, where they do all this type checking at runtime. C++ does it at compile time. So when the program is running, you're guaranteed that this is going to be correct because it's already done a lot of this checking for you. So what the compiler does now is it's going to check to see, does it make sense for me to assign whatever value is in here to here? How does it know? It's looking at the types. Okay, it's saying num2 is an integer, num1 is an integer. Okay, if I did something like num1 equals 200, it's going to say, okay, that's an integer. Does it make sense to assign an integer to an integer? Sure it does. It's got its rules internally. And we'll talk about mixed mode assignment and mixed mode math in a couple of videos from now. That's where we're adding and multiplying integers and real numbers and assigning potentially a real number to an integer. It's not just ints with ints, right? We've got different types working together. And that all works really well too, but we'll talk about that in a couple of videos. So that takes care of this. Hopefully you can see that conceptually it's really, really straightforward. Let's say that we wanted to chain these together. Okay, so what we can do here is we can chain those assignment operators together. And again, let's break this down so you can see what's happening. We're going to say num1, num2, and some value. It could be a big old mathematical expression, but in this case, I'm just going to use 1,000 to make things easier. Okay, so we've got two assignment operators here. What's important to understand with assignment operators and assignment expressions is that they return a value themselves. They return what was just assigned. Okay, and they associate right to left, which makes sense, right? In other words, this will be the last thing done. So the first thing the compiler does is it sees this expression right here. And it says, okay, I want to assign 1,000 into num2. Okay, let's do that. So num2 right here is going to get 1,000. Now the value that this expression evaluates to is 1,000 because that's the number that was just assigned. So now you've got num1 equals 1,000. So what we do is we assign 1,000 to num1. Okay, and now we're done. So you can see that you can chain these things together and they go right to left. So it's a handy way to initialize a bunch of variables to the same value. Again, we can have all sorts of expressions in here and so forth if we want. That's really not considered good practice. The only time that you really should even consider chaining these assignment operators is when you're assigning the same thing to everything. Right? Num1, num2, num3, num4 equals 10 or 0 or something like that. That makes sense. But if you've got really complicated expressions in these pieces here, that's probably not a good idea to do. Okay, so let's take a look at that and let's run this. And you can see now that when they print out, you get 1,000 and 1,000, just like you would expect. Num1 is 1,000, num2 is 1,000. Okay, let's do an error here. Let's say we wanted to do something like that. Now, the C++ compiler is pretty smart. And when we talk about classes and objects, we'll talk about how we can make the assignment operator our own so it works with our own classes. So as I said, C++ is pretty smart. It's going to try to see if it's possible to convert whatever's on the right-hand side to the left-hand side. In this case, you're telling the compiler, store a string, Frank, right, a sequence of characters, into an integer. That makes no sense. The compiler is going to try to see if it can convert that string to an integer somehow. And if it's got some sort of code that maybe you've written, it'll execute that code and convert it. In this case, there is no such code. So if I build and run this, I'm going to get an error. And the error is going to say invalid conversion from a character pointer. We'll talk about what that is in a few videos to an integer. So again, it's a conversion issue. It's saying, I don't know, these are apples and oranges as far as the compiler is concerned. So let me clear this and let's do one more. And let's say I want to assign 100 to num1. We've seen that works fine, but what if num1 is a constant? So let's say we made num1 a const. This shouldn't be allowed, right? Because you've just said I've got a constant integer here, number 1, and I initialized it to 10, and now you want to change it to 100. Obviously, the compiler is going to say, whoa, wait a minute, you just told me that was a constant. I can't do that for you. So let's try that. We'll run it, and you should see an error, something about read-only. There you go. Error, assignment of read-only variables not allowed. So you can't do that. Okay. Similarly, I can't do something like this. 100, let's say, equals num1. Right? What are you trying to do here? Your compiler is probably thinking, what in the world do they want to do? Okay, we know what num1 is, right? Its value, it's 10 because it's on the right-hand side. But now you want to assign it to 100. 100 is a literal. 100 doesn't have an L value. It doesn't have a location in memory. Okay? So when you run this, you'll see something like error L value required as the left operand of an assignment. I need to store this somewhere. I need a location. And 100 is a literal. It doesn't have a location. Okay, so that's it. Assignment at this level is pretty simple. We're going to use it at this level for a bit. Once we get to our own classes and objects, we can make assignment work for us in a really, really powerful way. And we'll talk about that when we get there. In the next video, what we'll do is we'll talk about the mathematical operators, or the arithmetic operators, the plus, the minus, the multiply, the divide, and the remainder. In this video, we'll go over C++'s arithmetic operators. These are exactly the ones you expect. The plus symbol means addition, the minus symbol means subtraction, the asterisk is multiplication, the forward slash is division, and the percent symbol is the modulo operator, or the remainder of division. You may not be familiar with this operator, but that's okay. We'll cover it toward the end of the video. The plus, minus, multiplication, and division operators are overloaded. What that means is they'll work with different types. So we can add 2 integers, we can add 2 floats, we can add 2 doubles by simply using the plus symbol. The same is true for subtraction, multiplication, and division. The modulo operator only works with integers. And again, I'll show you an example of that in a little bit. So let's try a few examples here. In the code down here, you can see that I've declared 2 integers, num1 and num2, and I've assigned 200 and 100 to them respectively. Again, these are integers. You could do this with doubles or floats or anything you'd like, but I'm just going to use integers here. You can see that this first line, this first output statement right here, let's walk through that really quickly so we're clear as to what's going on here. Remember, we've got expressions here. So num1 is an expression, num2 is an expression, and that addition expression is evaluated to the sum of num1 and num2. So in this case, num1 is 200, so this will be replaced with 200. Num2 is 100, and this will be replaced with 100. And then num1 plus num2 will be added together. That's why the plus is there, and this will give us 300. Okay, now these guys are inside quotes, so they're string literals, and they'll be printed out as is. So what we expect here is 200 plus 100 equals 300, and of course we've got the new line, or the end line at the end. All right, so let's run this and see if we get what we expect. And exactly that's what happens. 200 plus 100 equals 300. Okay, so let me comment that line out. And what we could do is, rather than do that calculation right in line right here, we could simply do the calculation and assign it to a variable. In this case, let's create a variable called result. And we'll initialize it to 0. And all we're saying is add num1 and num2, that'll give us 300, and assign that result to the result variable. Okay, so we're going to add 200 plus 100, that gives us 300, and we're storing 300 into result. And then rather than do the calculation here as we did, we're just going to print out result. Okay, it's as easy as that. So when I run this now, I should have the same exact output. 200 plus 100 equals 300. So now let me comment out some of these, and we'll walk through these real quick. And I'll do it right up to there. So this next one here on line 29, I'm simply subtracting num1 minus num2, storing the difference in result, and then I'm outputting result. So here we would expect 200 minus 100, we'd expect 100. On line 32, we're multiplying the two. This is different from algebra. You have to have that multiplication symbol, that asterisk. You can't just say num1, num2, something like that, like you would do in algebra. You just put the two things together. You can't use a dot like you could in algebra as well. It's got to be the multiplication operator, which is the asterisk. So we're going to multiply num1 and num2. That'll give us 20,000, which we store in result, and we're displaying that. And then the third one would be result is num1 divided by num2. That's on line 35, and we're going to store that quotient into result. There we would expect 200 divided by 100 gives us 2. Okay, so let's run what we've got right here and see what our results are. So we've got 200 plus 100 like we did before is 300. 200 minus 100 is 100. 200 times 100 is 20,000. And 200 divided by 100 is 2. Okay, so this is exactly like you would expect. It's really, really simple. Math works just like you expect it to. Now, something you may not expect is this result right here on line 38. I'm going to uncomment this. And in this case, what I'm doing is I'm dividing num2 by num1. Okay, remember, num2 is 100 and num1 is 200. So what's happening here is I'm dividing 100 divided by 200. You would expect 0.5. That's not what you get. We're doing integer division, okay? So there are no digits after the decimal point. We're working with whole numbers only. So in this case, what happens is 100 gets divided by 200. And the result, if these were doubles, would be 0.5. But we're working with integers, so this piece is just chopped right off. So we end up with a 0. Okay, so let's run this. And you can see here 100 divided by 200 is 0. You've got to be really careful when you're doing division with whole numbers or integers, because this is the behavior. If you need the 0.5, you want to be really, really precise, then you need to use doubles, not integers. And I'll show you an example using doubles in a second. Now let's look at the modulo operator, or the remainder of operator. In this case, right here, I'm saying num1 mod num2. Again, what's num1? It's 200. What's num2? 100. So 200 divided by, let me write that out real clear so it's not confusing at all. So we're going to say 200, right, divided by 100. The result of this is 2 with a remainder of 0. That's the modulo operator. It's only interested in the remainder. So in this case, it'll print out a 0. The next line, I'll uncomment that out in a second, but the next line we're going to say right here, num1, let me clear that, draw that line a little nicer there. Here we're saying num1 mod num2. So we're saying 10 mod 3. Remember, this only works with integers. So the result here of the division will be 3 with a remainder of 1. Remember, 3 times 3 is 9, and you get the 1 remainder. That's the result of the modulo operator. It's a pretty handy operator. So let me clear this, and I'll uncomment these few lines of code right here. And we'll run this. And let's take a look at the result. So here we go. 200 mod 100 is 0, right? That's the remainder, because we get a 2 with a remainder of 0. And in this case, 10 mod 3 is 1, because we get a 3 with a remainder of 1 when we divide by 3. This can be a really, really handy operator to use. And in the challenge exercise, you're going to have to use it to solve the problem. A couple more things. Just like you can with any programming language and doing any kind of math, we can add and divide and subtract, and we can do everything in line. It's important to understand that the precedence, or the order in which this stuff happens, is the same precedence you probably learned in grade school. Here in the US, we learned PEMDAS. That was the acronym we used, which meant parentheses first, then exponents, then multiplication and division, and then addition and subtraction. You may have learned something else if you're from a different country, but that's what we learned here. So what this means is that multiplication and division happen before addition and subtraction, right? So in this case, what's going to happen is num1 is going to be multiplied by 10, and then we're going to add num2 to that result, right? If you want something else, if you want to add the 10 and the num2 first, then you need to use parentheses around there like that. It's as simple as that, and it's something that we're all used to by now. Let me clear this, and then I'll do this last example with the division. I'll comment these 2 lines out. So in this case, I'm outputting 5 divided by 10. Remember, this is using integer division, so 5 divided by 10 is 0, not 0.5. In this case, 5.0 divided by 10.0 is 0.5 because we're using doubles here. In a couple of videos from now, we're going to do a video where we're mixing types. We'll be multiplying and dividing integers and doubles all together on the same expression. In that case, we can use casts to tell the compiler, hey, you know what? I really want this to be a double instead of an integer, even though it looks like an integer there. Okay, so we'll get to that in a minute. And let me run this thing one more time. And you could see the last 2 results right down here. 5 divided by 10 is 0, and 5.0 divided by 10.0 is 0.5. Okay, so now let's solve a real problem. Let's convert euros to US dollars. And I've created a project in the Section 8 workspace called Euros. This project that I worked on right here is called Arithmetic Operators, so you can refer to that if you like. But I've created a project called Euros, and that's the one we'll get to next. Okay, so I've opened up the main CPP file in the Euros project. Right now, there's really not much in here. I'm just printing a new line at the end to separate that little time message that is displayed at the end. And there's no real code here. We're going to write the code from scratch. So what we want to do is we want to convert euros to US dollars. So obviously we need some sort of conversion factor. I just went on Google now and I saw that you have $1.19 per euro. Okay, so 1 euro is $1.19. So we need to use that value somewhere. Now that's going to be a constant. So let's define that as a constant. We can do it right here. We could say const. We want it to be a double, right? Because it's not an integer, it's 1.19. And we'll give it a name. We'll call it US dollars per euro, per EUR. And we'll initialize that to 1.19. And don't forget the semicolon. So now we've declared that constant US dollars per euro to be 1.19. It's not going to change, even accidentally. Now, what do we need to do? Well, we need to output a message to the user. We'll say cout. We'll say welcome to the EUR to USD converter or something like that. And we'll print an end line at the end. We need to ask the user to enter the value in euros, right? I mean, that's the whole idea. So cout, we'll say enter the value in euros. And we'll do something like that. We won't put a new line there because we want the user to type something in right next to it. What do we do next? Well, we need to do a few things. We need, remember, most of these programs are input, processing, and then output. We need input. We need to read in from cin the number of euros that they want to convert, right? So we need to have something like cin into euros. So we need to define that variable right here. Right, so let's do that right in here. We'll say double. We'll call it euros. That's a good name. And we'll initialize it to 0.0. That way we know we've got a zero value in there. We know we're going to convert this to dollars, right? So we may as well create our dollars variable as well. So we could say double. And we can call it dollars. And again, 0.0. Perfect. Now we're right in the euros. We need to convert the euros to dollars. How do we do that? We just use a real simple multiplication. We can say that the number of dollars is equal to, again, the number of euros times the constant we have, dollars per euro. And now all we need is that final output statement. Let me scroll up just a little bit. And we'll say something like cout, and we'll say the euros, whatever they entered, is equivalent to, or we'll actually say euros, that'll be nice so I can read it better, is equivalent to, we'll put another insertion operator here, we'll type in dollars, whatever the conversion was, and then we'll just type the string dollars so it's nice and readable. That's it. We'll put a new line at the end with end line, and that should be it. Let's run this and see if we have any errors. We'll test it to make sure we don't have any errors, and we'll debug it if we do have any errors. All right, so I'm going to save, and I'm going to press Control F5 to run. There's no compiler errors, so that's great. So enter the value in euros. Well, let's type in €1, right? If we type in €1, we expect back $1.19. So that would be a real simple and good test case. We get €1 is equivalent to $1.19. Good. Let's try another one. Let's run. How about 123.5 euros? We get back $146.965. Don't worry about the precision and the dollars and cents. We'll learn how to format output a little bit later. That's it. That's the program. Really, really simple. You can see that what we're doing here is we're using the things that we've learned, right? We're using our cin, we're using our cout. We've got a constant defined right here. We've got some variables that we need here, and we're initializing them to 0. And we're doing our calculation here using one of the arithmetic operators, the multiplication symbol. I encourage you to write one of these programs on your own. Write a something to something converter, Fahrenheit to Celsius, kilometers to miles, yards to inches, meters to centimeters. Write one of these programs just like that. That'll give you a good practice. In this video, we'll go over C++'s increment and decrement operators. I'm in the Section 8 workspace in the increment-decrement operators project. This is a pretty simple looking operator, but there's a lot to it, and it can be extremely confusing if you overuse it. Let's talk about it. Basically, it's the plus plus and minus minus operator. You've got two pluses side by side or two minuses side by side. All that means is increment something by 1 or decrement something by 1. In this example, I'm only going to be using the increment operator, but everything will apply to the decrement operator. Okay, so all it does is increment or decrement its operand by 1. So if you use it with an integer, it increases the integer by 1 or decreases the integer by 1, depending on which one you're using. If you're using it with a floating point number, same thing. It'll increase it by 1 or decrease it by 1. And we can also use it with pointers to move pointers along. We haven't talked about pointers yet, but we'll use this operator when we talk about pointers in a future section. There are two variants to this operator. There's a prefix notation and a postfix notation. All that means is that the operator is either before its operand or after its operand. You can see here on line number 9 that the operand is num and the operator is to the left of it. So that's prefix notation. The postfix notation is when it appears to the right of the operand. Okay, I'll say this a few times. Don't overuse this operator and never use it twice for the same variable in the same statement because the behavior is undefined. You really don't know what you're going to get. Good. So now let's talk about the operator. Let me scroll down just a little bit. And I've got some examples here, and I'll walk through these examples really, really carefully and slowly so you can understand what's going on. For all of the examples, I'll be using these two variables right here. I'll be using a variable called counter and a variable called result. They're both integers. Counter will be initialized to 10 and result to 0. Okay, so real straightforward. Counter will be 10, result will be 0, and we're going to manipulate those variables, and we'll see how this operator really works. So let's start right here. Let me uncomment example 1. I'll walk through this really slowly. You can see what's happening. I'm outputting counter. Okay, well, counter is 10, so this you expect it to display a 10, and that's exactly what happens. In this case, I'm saying counter equals counter plus 1, right? So what's counter? 10. I'm adding 1 to it, and then I'm putting it right back into counter. So I'm changing this to an 11. And this output statement will display an 11. In this case, I'm using counter plus plus. That's the increment operator. That's going to increment the variable counter by 1. When you use it all alone like that, if you've got an operand followed by a plus plus or a plus plus before the operand, it means exactly the same thing. All it means is increment the operand by 1. Okay? It'll get a little more confusing in the next few examples, but let's just get this one under our belt so we can understand what's going on. So what's happening here is we're incrementing that L value counter by 1. So we're going to counter, incrementing it by 1. Now it's 12. And we're going to display counter here, which is 12. The pre-increment works exactly the same as the post-increment when that thing is all alone on a line, just like I said over here. So in this case, exactly the same thing will happen. I'm going to take the 12 and add 1 to it, make it a 13. Counter will now be 13, and I'll output 13. All right, so in this context, wherever you want to increment something, you could say counter equals counter plus 1, or you could just say counter plus plus, or you could say plus plus counter. All three of them mean the same thing. Later on, we'll talk about a different operator, the plus equals operator, that does the same thing as well. So there's a bunch of different ways that you can achieve the same result. I'm going to clear this, and remember, we've got 10, 11, 12, and 13 as the output. So I'll clear this, and let's run this example. And you can see that counter is 10, 11, 12, and 13, just like what we expected. All right, so now let's look at a little bit more complicated example, and I'm going to comment this out, and I'll comment this out, not delete it, and I will uncomment out example 2. Okay, so let's go through this one again really carefully. What we've got here is, again, I've reset counter to 10 and result to 0. All of these examples are going to start in the same place. Counter will be 10, result will be 0. So here I'm going to say I want to output counter. Well, counter is 10, right? So we expect this to display a 10. Now we're doing a pre-increment of counter, and we're storing the result into that variable called result. So what's happening here is there's really a few things going on here. If you just see that plus plus and just take it out for a second, and the result is something like this. Result equals counter. That's the real assignment statement that's going on here. The plus plus in front of counter means it's prefix notation, which means that counter will be incremented before it's used. So in this case, before happens here. Its use is right here, but before it's used, we're going to say counter equals, I'll just say counter plus 1 just to be really explicit. So this statement right here, that's the effect of that statement. I want to increment counter before I use it, and then I want to use it by assigning it to result. All right, so let's do those 2 steps and see what happens. Counter equals counter plus 1. We just made counter 11. And then we're going to assign counter to result. Well, counter is 11, so result will now be 11. Now I want to display counter. Counter will be 11, and result will be 11. So this is what I expect as the output, 10, 11, and 11. Okay. Remember, this is the use, and this is the effect of that pre-increment. All right, so let me clear this and run it. Again, we're expecting 10, 11, and 11. I'll build and run, and there it is, 10, 11, and 11, exactly what we expected. All right, I'll comment out that piece, and we'll do another example, this time with a post increment. And remember, I'm using the increment, but the decrement works exactly the same way. It just decreases the value by 1. All right, I'll uncomment this example, and let's walk through this one again. One more time, I'm initializing count, or I'm assigning 10 to counter and 0 to result. And I'm saying print out the counter. Well, it's 10. We expect a 10 here. That's an easy one. But now we're doing a post increment. Notice it's on the right side, or it's following counter, its operand. So this becomes result equals counter. And the post increment simply means that we're going to increment counter after we use it. Well, we're using it here, so let's increment it after this time. So again, I'll be really explicit here, and I'll say counter equals counter plus 1. So that's the effect of that statement. So let's execute this statement. Result is counter. Well, counter is 10, so let's put 10 in here. Now we increment counter by 1. So that becomes 11. And now we display counter, which is 11, and result, which is 10. So in this case, this is the output we expect. 10, 11, and then 10. All right, let's give that a shot. And there we go, 10, 11, and 10. Let's do a few more examples, so I want to be sure that you really understand this. Let's uncomment example 4 here. And example 4 just uses the expression that's a little bit more complicated. Not much, but a little bit, so you can see how this works. In this case, one more time, I've set those to 10 and 0, and I'm displaying counter. Well, counter is 10. Again, real easy. And now we've got this statement going on right here. Result equals plus plus counter plus 10. The best way to really look at these things is just get rid of that guy right now. So just say result equals counter plus 10. That's the statement. And now, since the plus plus is a pre-increment, it's on the left side of counter. That means that we increment counter before we use it. We're using it here, so that means that we do this before we execute that statement. So again, counter equals counter plus 1. All right, so let's do this. Counter is counter plus 1. This becomes 11. Then we say result is counter plus 10. Well, counter is 11. So 11 plus 10 is going to give us a 21, which we're going to store in result. So result here, we'll get a 21. Got it? Perfect. Now, we're displaying counter. It's 11. Result is 21. That's what we expect to display. 10, 11, and 21. This may seem a little contrived and puzzle-like, and it may be, but this kind of code is seen out there, and you really need to understand the effect of the pre-increment and the post-increment with these operators. So 10, 11, and 21 is what we expect. Let's run this. And 10, 11, and 21 is what we get. Okay, so let's comment this one out. And you'll notice what this one, the next one, example 5, is exactly like example 4, except we've got a post increment right here. Right there, you can see it's the same idea, except it's the plus plus is after the operand. Okay, so again, 10 and 0, we're starting out. We're saying display the counter. Well, the counter is 10. That's pretty easy. Here's the statement. Let's just rewrite it without the increment. So we're going to say result equals, again, counter plus 10. I'm trying to write nice and big, so hopefully everybody can see this okay. And we're doing the increment of counter after we use it. That means after we use it. We're using it here. So this becomes counter is counter plus 1. All right, so let's execute these two statements. We'll put some semicolons there just to be complete. So result is counter plus 10. Well, what's counter? Counter is 10. So that becomes a 20, and we're storing 20 into result. And then we're incrementing counter by 1, so counter becomes 11. Okay, the output says what's counter? 11. What's result? 20. So in this case, 10, 11, and 20 is what we expect. 10, 11, and 20. Let's run this. And 10, 11, and 20 is exactly what we get. Okay, so hopefully that clears it up. And one of the examples, if you remember up at the top, I mentioned, I'll scroll up a little bit, it says here, never used it twice for the same variable in the same statement. That could be something like, suppose you do cout, and you've got something like, I don't know, let's just say we have an integer I. You'll say I plus plus, and then you'll do something like plus plus I. And something like that, you really have no clue what's going to happen because you're incrementing I 2 times in the same statement, and that's not a good idea. Sometimes you'll see people do silly things like I plus 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 I or something like that, just because you can in C++. But that's a bad thing to do because you're using it twice on the same variable in the same statement. And that behavior is totally undefined. So your guess is as good as mine as to what the result is going to be. Okay, so hopefully this gives you a little bit of insight into this operator. It's a simple operator when you just say I plus plus or count plus plus or plus plus count. Really, really simple. But when you start combining it with other operands and other expressions and operators, it can get pretty complicated. And that's why I say don't overuse this operator. It's really a great operator to use when we loop, and we'll do that later and when we use pointers, but keep your eye on it. Don't overuse it. In this video, we'll learn about mixed type expressions. This is when you have an expression where the operands are of different types. For example, a plus b, where a is an integer and b is a double. C++ is very consistent with its application of an operator to operands. The operands must be of the same type. As we'll see in the next few slides, it's very important to understand the rules that C++ uses to ensure that the types are the same, since the results of the calculation could be different depending on which operand type is changed. C++ will try to convert one of the operands so it matches the other. In many cases, this happens automatically, and we'll talk about how that works in the next slide. If an automatic conversion or coercion is not possible, then a compiler error will occur. We saw an example of this in the assignment operator video when we tried to assign a string to an integer. In order to understand how these conversions happen, we need to understand higher versus lower types. The idea is simple. The lower types are those types that can hold smaller values, and the higher types can hold larger values. So a long double is of higher type than a long, and a long is of higher type than an int. The idea is that we can typically convert from a lower type to a larger type automatically, since the lower type's value will fit into the higher type's value, but the opposite may not be true. Short and character types are always converted to integers. So let's learn the terminology. A type conversion is also called a coercion, since we're coercing one type to another. Sometimes this happens automatically, and sometimes we do it ourselves in code. Promotion is when we convert a lower type to a higher type. An example would be when we add an integer and a double. In this case, we promote the integer to a double and then do the calculation. Demotion is when we convert a higher type to a lower type. Suppose we want to store 12.5 into an integer variable. It won't fit. So a demotion happens and the decimal part of 12.5 is truncated, and we're left just with the integer 12. Let's see a few examples. In the first example, we have two different types and an operator. You can think of the operator as the multiplication operator, but it applies to any operator. In order to perform the multiplication, the compiler will convert the lower type to the higher type and then perform the multiplication. You can see in the example where we multiply the integer 2 and the double 5.2. In this case, we can promote the lower type, which is the integer 2, to the double 2.0 and then perform the multiplication. In the second example, we're assigning a value from a higher type to a lower type. In this case, the compiler demotes the higher type to the lower type, potentially losing information. Many compilers will warn you about the possible loss of precision, but not all do. In this example, we have num as an integer, and we assign a double 100.2 to num. 100.2 will be demoted to the integer 100, and 100 will be assigned to num. As mentioned previously, the C++ compiler will try to do automatic coercion when it can. However, as programmers, we can explicitly tell the compiler to cast to a specific type if we wish. Let's see how. So let's talk about how we can tell the compiler to coerce or cast one type to another. Let's walk through this example. You can see we have two integer variables. Think of total amount as a running sum of several numbers, and we want to know the average of those numbers. So we need to know how many numbers there are. In this case, this is represented by the integer total number, which is 8. The average in this case would be total amount divided by total number, which is 12.5. But since both of these variables are integers, the compiler will do integer division and the result will be 12. That's not what we want. We could change the type of total amount to double, but we're modeling a running total of integers, so an integer type is more appropriate. The solution is for us to tell the compiler to cast or perform a coercion of total amount from integer to double. The syntax is to use static underscore cast, followed by the type we want to convert to in angle brackets, and then the variable name in parentheses. Now one of the operands is a double, so the compiler will automatically convert the total number to a double and do double division, which is exactly what we want. Now we get 12.5, which is the result we wanted. Let's head over to CodeLite and write a program that asks the user for 3 integers and computes their average. Okay, so now I'm in the CodeLite IDE. I'm in the Section 8 workspace in the Mixed Expressions project. So let's write a program here that asks the user to enter 3 integers. We calculate the sum of those integers, and then we calculate the average of the integers. All right, then at the end, we'll just display the 3 integers that were entered, the sum of the integers, and the average that we calculated. All right, so let's get started. We have an empty main here, and I'll scroll this up so we have a little bit more room to work. And we know we need a total, right? We need to sum up those 3 numbers, but we also need to store those 3 numbers. So let's create those variables first. We'll create a total variable. And again, the names you use could be anything you like, and we'll zero that out. And we'll create 3 variables for the numbers that we're going to enter. We'll call them num1. And I could do this and do each one on each line, but what I'm going to do is I'm just going to do them all in one line. So I'm going to say num1, and I'm going to say num2. And finally, I'll say num3. This initializes all 3 of them to 0. If you don't do it this way, or rather, if you do it this way, and you don't put those initializers there, then num3 will be 0, and num1 and num2 will be undefined. So if you do it this way, be certain that each one of them gets its own initializer. So that's it. We've got our 3 numbers. We've got our total, and we also need a count, right? We're going to have 3 numbers, so we may as well define that integer as a const, and we'll call it count. And again, we'll initialize that to 3. That way we know we're not going to make any silly mistakes. Great, so let's prompt the user. We'll say cout, and I'll just say enter 3 integers separated by spaces. That way they could just type them in on one line, and we don't have to do 3 prompts. And we'll just leave it at that. Don't forget the semicolon at the end. We don't need an end line here. Now we're going to read all 3 integers. So we'll do cin, we'll use the extraction operator, num1, and we'll just chain them together, num2 and num3. All right, so now we've got all 3 of our integers. We need to total them up now, right? We need to sum them all up. So we've got our total variable. So we'll just say total is num1 plus num2 plus num3. All right, so now we've got that. Now, obviously we could have total be a double, but it really makes sense for it to be integers because we're adding up integers, so the total should be an integer. So now let's calculate the average. We need a variable to hold that, so that will be a double, and we'll just call it average, and let's initialize that to 0.0. That way we know we've got a known value in there. Great, so let's do the calculation now. Average, and I'm just using some blank lines here just to separate them. Normally you wouldn't write all these blank lines, but I just want to write them so you can really see what's going on. So I'll say average is the total divided by count. That's it. And now we've got our output statements. We'll say, let's just say something like the 3 numbers were, and we'll display all 3 numbers here. We'll say num1, we'll put a comma here, we'll say num2, we'll put another comma, and finally num3, followed by the end line. Next statement we'll say the sum. The sum of the numbers is, and obviously that is our total variable. So we'll display total here. And again, we'll follow it by an end line. And then finally, the average. There's my last output statement. And we'll just say the average of the numbers is, and again, average. Okay, so far so good. End line, that's it. Let's compile this and see if we've got any compiler errors that we have to fix. Okay, no compiler errors, it runs. So let's run this. Enter 3 integers separated by spaces. How about 10, 30, and 20? Right, that's 40, 50, 60. 60 divided by 3 is going to give me 20. So I expect that to be the average. I'll press enter. The output says the 3 numbers were 10, 30, 20. That's correct. The sum of the numbers is 60. That's correct. The average of the numbers is 20. That's also correct. Okay, one more test case. We'll say 10, 20, 15. In this case, we've got 45. The average is 15. Good. We're done. No, we're not. Program has a pretty big problem in it, and we saw that in the slides. Suppose that I run it again with a different test case, something like 10, 20, 20. In this case, it's 50 divided by 3, which is 16.667. Instead, I'm getting 16 because I'm doing integer division. This is why testing your program is so important. We'll talk about testing as we go through the course, but testing your program is important, and testing involves knowing what the result is before you run your program, right? So in this case, have some test cases ready, maybe 0, 0, 0, something that is divisible evenly by 3, another test case that isn't divisible by 3, and so forth, okay? So how do we fix this? Well, what we can do is we can cast that guy or this guy, either one, to a double. Okay, and we'll use the static cast. So we'll say static underscore cast. Then in the angle brackets, we put in the type that we want to cast to. In this case, I want to cast it to a double or convert it to a double. And then we put total inside parentheses. That's it. Now what's going to happen is the compiler will convert total to a double. The compiler will say, oh, I've got a double and an integer here, so I'll convert the integer to a double as well and do double division, which is what we want. So let's run this again, and let's use that same test case, 10, 20, 20. And now we've got the correct average here. Okay, now before I finish this video off, in older C code, instead of seeing this static cast here, you might have seen something that looked like this. Something like that, then total divided by count or something like that. Okay. This is the old C style cast. The static cast is what we want to be using in modern C++. It's a little bit more restrictive than this kind of cast. This kind of cast just assumes that whatever total is going to be converted to a double. The static cast double checks to make sure that it can be converted to a double. So you don't want to do this. I'll just write here as a comment, old style, just so if you've seen it, you'll know what it's all about. Okay, so that's it. That's the example. Pretty straightforward. We're defining some variables. We're getting some input. We're doing some calculations, and then we're checking that calculation to be sure it's correct. In this case, I've got integer division. I've got to make one of those a double, otherwise I'm not going to get the right result. Okay, that's it for this video. In this video, we'll go over the C++ equality operators. These operators compare the values of two expressions and evaluate to a Boolean. That's a true-false value. The operators are the equals, which is represented by two equal signs, and the not equals operator, which is represented by the exclamation point or bang symbol, followed immediately by an equal symbol. Be extra careful when you're starting. It's super common for beginning C++ programmers to use a single equal sign. That's assignment, not comparison. These simple operators, along with the operators we'll learn about in the next several videos, give us so much power in programming. We use these operators all the time in control flow statements that we'll learn shortly. So suppose we want to do something when x is equal to 100. We can do that. We can also test for two expressions not being equal. So if my password doesn't match the password on file, then you want to do something specific. The following code snippets only show the equality expressions. They're always used within statements. The first example evaluate to true if the value of expression 1 is equal to the value of expression 2. These two expressions could be very complex or very simple. The second example will evaluate to true if the value of expression 1 is not equal to the value of expression 2. The third example will always evaluate to false, since 100 will never equal 200. We don't usually write expressions like these, but it serves to illustrate how this operator works. The final example evaluates to true if num1 is not equal to num2. Let's go over a few more examples that use statements. First, we're declaring a variable named result that's of type Boolean, and we're initializing it to false. Then we compare 100 and 50 plus 50 for equality. This will result in a Boolean that's a true-false value, which we assign to result. In the next example, we compare num1 and num2, and if they're not equal, we store true in result, otherwise false. Notice how we can use Boolean expressions in output statements. In the first output statement, we're comparing num1 and num2, and we're displaying 1 if they're equal or 0 if they're not equal. Sometimes it's handy to display the words true and false rather than 1 and 0 in the output statements. We can do that using the bool alpha stream manipulator. Bool alpha and no bool alpha are located in the standard namespace. Once you use them, all Boolean output to the stream will result in the words true and false being displayed. That can be pretty handy. If you want to go back to the default of 0 and 1, just use no bool alpha. Let's head over to CodeLite and see some examples. So I'm in CodeLite. I'm in the Section 8 workspace, the Equality Operators project. Let's run over a few examples of using these equality operators. These are going to be really straightforward examples. I don't think you'll have any issues understanding these, but you may see a couple of surprises, so stay tuned for that. So here we go. We've got a Boolean called equal result, which I'm initializing to false, and another Boolean called not equal result, which I'm also initializing to false. And I've got two integers here, num1 and num2, and we'll just play around with this a little bit. I've got my cout bool alpha here commented out. I'll uncomment that out in a moment so you can see the difference between the behavior when you do that. So here I'm prompting the user to enter two integers separated by a space. I'm reading in those two integers on line 15. I'm comparing those two integers for equality right here on line 16. So I'm saying is num1 equal to num2. That result is going to be stored in equal result. So it's either going to be true if they're equal or not true if they're not equal. Then I'm going to compare the same two numbers using the not equal operator. So is num1 not equal to num2? In this case, if they are not equal, then I'm going to store true into the not equal result. Otherwise, false. Okay? And then I'm just going to print out those two results. So let's run this piece of the code right now, and you'll see what happens. Let's enter two integers. In this case, let's enter two integers that are equal to one another. So I'll type in 10 and 10 and press enter. And you can see here the comparison result for equals is 1, which is true. And for not equals, it's 0 because they obviously are equal. Okay, now notice I have a 1 and a 0 being outputted here. When I uncomment out the bool alpha stream manipulator and recompile and run, now I can say, let's say 2020. And instead of 0 or 1, we see true false. So that's pretty handy. So in this case, they are true, so the equals will be true and the not equals will be false. Now let's use an example where they are not equal. And let's say we're trying to do 10 and 20 this time. So equals is false and not equals is true, just like what we'd expect. Okay, so like I said, that's pretty straightforward. I'm going to comment out this piece of code right here. And now we'll do the same thing, except we'll do it with characters. Remember, we can do this with any type. We can compare any type. So in this case, I've declared two characters, char1 and char2, and initialized them both to empty, to 0. And I'm asking the user to enter two characters separated by a space. I'm reading in the characters. Then I'm doing exactly the same thing. I'm comparing them for equality, and I'm comparing them to see if they're not equal. So let's run this. And the first test we'll do is we'll say lowercase a and uppercase a. Those are different characters. I'll press enter. Are they equals? Nope, that's false. Are they not equals? True, that's true. So that's exactly what we expect. And let's test it one more time with, let's say, a capital Z and another capital Z. In this case, they are equal. So that's true, and the not equals is false. Okay, so you can understand the logic that's going on here. I'll comment that out, and I will uncomment the next section, which is dealing with doubles. So again, exactly the same thing, except I'm using doubles. I'll run this, and we'll type in, let's say, two doubles that are the same, 12.1 and 12.1. The comparison result is they are equal. Exactly what we'd expect again. And let's do an example where they are not equal. So let's say 12.5 and 13.2. The equals is false because they're not equals, and the not equals is true because they are not equals. Okay? Now, this is the example that I wanted to run to show you something that may not be real obvious. Let's say we want to enter two doubles separated by a space. So I'm going to type in 12.0, and 11 point, lot of nines. Now to us, those are not the same number. But remember the way the computer stores floating point numbers, it stores approximations. So that might be surprising. As far as the computer is concerned, those numbers are equal because the representation that it's using to store them behind the scenes is equal. Okay, so it's important to understand that. If you're dealing with applications that need this kind of precision, scientific application, medical applications, many safety critical type applications, you would not use these built-in doubles. We would use specific specialized libraries that really help us deal with this so that 12.0 is not equal to 11.99999. Okay, so it's important to understand that, but the way that it stores it is an approximation. So as far as the computer is concerned, these are the same. So let's do one more, and I'll leave that double declaration there, and I'll uncomment this last piece of code here. And here I'm just grabbing an integer and a double. So we're doing some mixed mode comparison here. I'll run it. And it says, give me an integer and a double separated by a space. In this case, I could say 10 and 10.0. Remember what happens. It's using an operator to compare two different types. It doesn't want to do that. Those types have to be the same. So the 10 will be promoted to a 10.0. And then the comparison happens. That's the mixed mode expressions. So what we're doing here is we're eventually comparing 10.0 and 10.0. So we expect this to be true. And it is right there. And you get the same sort of issue here if I say 10 and 9.999, a whole bunch of nines. What's going to happen again is the 10 will be promoted to 10.0. 10.0 and 9 point, a bunch of nines, as far as the internal representation is concerned, are equal. So there's your true. Okay, so that's it. That finishes off this video. And that's it. I'll see you in the next video. In this video, we'll look at C++'s relational operators. In addition to the equality operators, C++ also has several other relational or comparison operators. These are greater than or equal to, less than, and less than or equal to. And in C++20, there'll be a really neat three-way comparison operator. This operator compares two expressions and evaluates to 0 if they're equal, less than 0 if the left-hand side is greater than the right-hand side, and greater than 0 if the right-hand side is greater than the left-hand side. Like the equality operators, these operators are very intuitive, easy to use and understand. Let's see a few examples in CodeLite. I'm in CodeLite. I'm in the Section 8 workspace, and this is the Relational Operators project. In this project, I'm just using some really simple examples to test some of these relational operators. As you can see, I've got two numbers declared, num1 and num2. This is where I'm going to read some integers into. And I'm asking the user to enter two integers separated by a space, and I'm reading those two integers from the user. Okay. Then what I'm doing in this output statement right here is, suppose that the user entered 10 and 20 here. I'm just saying 10 greater than, I'm just explicitly printing out that greater than sign, 20, and then I'm evaluating whether num1 is greater than num2, and that's going to say true or false. So it's going to do that for all four operators, greater than or equal to, less than, and less than or equal to. And then we could try out a couple of examples with this program. So let's run it. And let's enter two integers. Okay, so let's enter 10 and 20. So you could see here, 10 greater than 20 is false. 10 greater than or equal to 20 is false. 10 less than 20 is true. And 10 less than or equal to 20 is also true. Okay, so now let's try some other ones. A couple of other test cases here. Let's try 20 and 20. In this case, you can see that 20 is not greater than 20. 20 is greater than or equal to 20. 20 is not less than 20, and 20 is less than or equal to 20. Just what we'd expect. So real simple example. What I'll do now is I'll comment out those output statements that we just did here. And I'll declare a couple of constants here, and I'll uncomment this piece of code out, and I'll walk you through it. So in this case, I'm declaring two constants, lower and upper, to be 10 and 20. And I'm asking the user to enter an integer that's greater than lower. So in this case, I'm asking them to enter an integer that's greater than 10. And I left those as constants so you can modify them here and play around with this program yourself. So in this case, enter an integer that's greater than 10. I'm reading that integer into num1. And then I'm comparing to see if that number is greater than the lower limit, which is 10 in this case. Then I'm doing the same thing. I'm saying enter an integer that's less than or equal to the upper limit. So let's run this. And first thing you'll see is it says enter. Oops. Let me get rid of that. Let me get rid of that statement at the beginning here. And we try that again. Here we go. So enter an integer that's greater than 10. So let's print 12. And it says 12 greater than 10 is true. That's what we expect. Now it says enter an integer that's less than or equal to 20. Let's put in 12. And it says 12 less than or equal to 20 is true. Okay, so let's run this one more time with a different test case. So enter an integer that's greater than 10. Let's put in 8 this time. And it says 8 greater than 10 is false. Obviously, I didn't do what I was told to do. And here, enter an integer that's less than or equal to 20. Let's put in 25. And we can say 25 is less than or equal to 20 is also false. Okay, you can see where we're going with these operators. Once we get to control flow statements, you'll have all this knowledge under your belt, and you'll really be able to write some really powerful programs that solve problems. In this video, we'll learn about C++'s logical operators. These operators allow us to build complex conditions in our programs. C++ has 3 logical operators. These are not, and or. These operators work on Boolean expressions and evaluate to a Boolean value themselves. There are several ways to write these operators. You can use the keyword-like syntax using the words not, and or. Or you can use the operator symbol syntax using the bang sign, the double ampersand, and the double pipe symbol or the double vertical bar. Personally, I've never seen any C++ code that uses the keyword-like syntax, so I'll use the operator symbol syntax in this course. Let's quickly review Boolean algebra by using a truth table. The logical not operator simply negates the result of the expression it's applied to. Note that this is a unary operator since it only works with one operand. So if the expression A is true, then not A is false. And if the expression A is false, then not A is true. Let's look at the logical AND. The logical AND is a binary operator, and it's only true when both its operands are true. So you can see in the table when expression A is true and expression B is true, then A and B is true. A and B is false for all other combinations. Finally, let's look at the logical OR. The logical OR operator is also a binary operator. The value of the logical OR is true when either expression is true. So the only time it's false is when both expressions are false. Using just these 3 logical operators, we can write some pretty complex logic. And if we combine the logical operators with the relational operators, we're in great shape to begin to solve many, many problems. Let's see what happens when we combine these operators together in an expression. Just like we had to understand precedence with the mathematical operators, we need to understand precedence for the logical operators. Logical NOT has the highest precedence, followed by logical AND, followed by logical OR. Of course, as with mathematical expressions, you can use parentheses to achieve exactly the behavior you're looking for. Let's wrap up logical operators by looking at a few example expressions and then talking about something called short circuit evaluation. Here are a few examples of logical expressions. In the first expression, we're determining if num1 is greater than or equal to 10 and less than 20. Notice that we use num1 in both expressions. We can't just write num1 greater than or equal to 10 and less than 20. We have to write num1 greater than or equal to 10 and num1 less than 20. Since we have an AND, both expressions must be true for the entire expression to be true. In the next logical expression, we're using a logical OR. In this case, either expression or both can be true for the entire expression to be true. So if num1 is less than or equal to 10, then the entire expression will be true. Also, if num1 is greater than or equal to 20, then the entire expression will be true. Notice how both expressions cannot be true, since num1 cannot be less than 10, and it can't be greater than or equal to 20 at the same time. The next logical expression is checking if it's not raining and the temperature is greater than 32 degrees Fahrenheit. The following expression uses a logical OR, and it will be true if it's raining or if it's snowing. Finally, the last logical expression is checking to see if temperature is greater than 100 and it is humid or it's raining. Remember here that the AND has precedence over the OR. I think you can see how powerful our logical expressions can be by simply combining these primitive operators. Also notice how important our variable names become as well. Let's finish up by discussing short-circuit evaluation. C++ will stop evaluating a logical expression as soon as it knows the result. For example, suppose we have an expression like the first one, expression 1 and expression 2 and expression 3. If expression 1 is false, then there's no way that the entire expression can be true, since all the expressions must be true. So why bother evaluating expression 2 and expression 3 when the compiler already knows that the result will be false? This is called short-circuit evaluation, and it's commonly used in many programming languages. Programmers take advantage of this behavior to optimize their code. In the second example, if any of the expressions is true, then the entire logical expression is true. So if expression 1 is true, then the compiler already knows that the entire expression is true, and it won't evaluate expression 2 or expression 3. However, if expression 1 is false, then the compiler continues evaluating expression 2 since it doesn't know the result yet. We'll use logical operators in depth when we learn about control structures. But for now, let's head over to CodeLight and see a few simple examples in live code. I'm in CodeLight in section 8 workspace, and I'm in the logical operators project. In this project, we'll go over a few examples of using logical operators. Let's start with a really simple one here. What I've got is I'm going to use this variable num to read numbers into just simple integers. I'm going to establish a range where the lower end is 10 and the upper end is 20. So that'll be like a number line where this will be 10 here and this will be 20 over here. Now I'm going to ask the user to enter an integer and tell them what the bounds are, 10 and 20 in this case. Then I want to be sure that that number they entered is within the bounds. And I just want to display true or false if it's within the bounds. And what we're doing here is we're going to say not inclusive of 10 and not inclusive of 20. Okay, so it's going to be 11 to 19 inclusive. All right, so that's what we're going to do. Now, we're going to store that true false value in this variable right here called within bounds. And here's our formula. Here's our expression right here. Basically, we're going to check to make sure that num is greater than lower. So num is going to be greater than lower. So suppose that user typed in 15. We want to make sure that it's greater than lower, and we want to make sure that it's less than upper. So we want to be sure that it's in here somewhere. Right? So that's where we've got that logical AND condition. So we'll do that, and then we'll simply print out the number is between lower and upper, and then true or false. And we can just display within bounds here. So let's run this with a couple of test cases. And here we go. Enter an integer. The bounds are 10 and 20. Now let's enter an integer that is within those bounds. 15 is right in the middle. And we'll press enter. And the result is 15 is between 10 and 20, true. Okay, so let's run another test case. Let's go off the right side to 22. Now we would expect a false. 22 is between 10 and 20, false. Let's do a test case on the left side. We'll go 5. We also expect a false. And that's what we've got. And then don't forget to test those edge cases, the 10 and the 20. So let's try 10. We expect false, right? Because being on 10 is not being between 10 and 20 in this case. So I get back a false, and the last test case we could run is 20. And we also expect a false, and that's what we're getting. It's very common to have these errors where instead of checking greater than here, you're doing greater than or equal to when you should be doing greater than and so forth. So you've got to be sure to test your code. Okay, so that's a simple example of testing to see if a number is between two numbers. Now, let me comment that out, and we'll do another example here. And of course, we're assuming that lower is less than upper in all of these examples. Okay. Now, what we want to do on this one is we want to test to see if the number is outside the bounds. Okay, so I want to be true if the number is outside the bounds. So we'll do the same idea here, right? We've got the line, and here's the 10, and here's the 20. And if the number's over here somewhere, we want a true, and if the number's over here somewhere, we want a true. Okay. Now we could just simply negate the previous result, right? So if the number is in here, if the number is not in here, then it's obviously either here or here. Right? But what we'll do is we'll do it explicitly. We've got a variable called outside the bounds, and we're going to check to be sure that number is less than lower. So that's taking care of this bit right here. Or number is greater than upper. There's no way we can use an and here. That would be a mistake, right? Because the number will never be less than 10 and greater than 20. That won't happen. It's impossible. So that would be a mistake, and that's a pretty common mistake, but you'll find it when you test. And there's your or. So let's run this example. And in this case, the bounds are 10 and 20. So let's say we want to go 25. Now, we expect true now. And that's what we're getting because 25 is outside of 10 and 20. Let's try the lower end. Let's try 5. That's also true. And let's try a number in between. 15 here. We expect that to be false, and it is because 15 is not outside the range. And then we could test with 10 and 20, and I'll leave that up to you guys. Okay, so let me comment that out. And the third example is actually checking to see whether the numbers are right on the bounds, whether they're 10 or 20. So what we're doing here, again, is we've got the line, got our number line, and we've got 10 over here and 20 over here. And we want to be sure if we want to return true if it's 10 or if it's 20. Okay, right on the bound. So we've got another variable here called onbounds. I'm setting it to false. And the condition is really simple. If the number is equal to the lower, that's it. So if the number is 10 or the number is equal to the upper. Okay, so if we've got a 10 or a 20 in this case, because that's what lower and upper are, this will return true. Remember, it can't be 10 and 20, so we need the or here. And with the or, if either piece is true, the entire thing is true. So let me clear this, and we'll run this example. So we should get back true for 10 and 20. So here's 10. There we go. We've got a true. We'll run it again with 20. That also gives us true, and everything else should give us a false, right? No matter what we put in. Let's put 15. We could put a false, and you could use some test cases outside 20 and less than 10 to check it out as well. So hopefully you're with me here. That's pretty straightforward stuff, but pretty powerful stuff. This is how you do input validation. You're asking a user to enter a number between something and something, or enter the amount of your check. Obviously, they're not going to enter negative numbers, and there may be a limit as to the upper end, so you can validate your data, because if you have bad data, you're going to get bad results. Now, in this case here, I'll comment all of this out, and I'll go through it and explain it to you. Okay, so what we've got here is and let me comment that bit out as well. All right, so here's where we're at. Here's the idea. We want to determine if you need to wear a coat, and that determination is based on the temperature and the wind speed. So I've got a Boolean value, and that Boolean value right here is going to be wear coat. That will be true or false, whether you need to wear a coat or not. And I'm going to read two variables in from the user. I'm going to read the temperature in Fahrenheit and the wind speed in miles per hour. And here are my limits. So wind over this value requires a coat. So if the wind is over 25 miles an hour, I need a coat. And the temperature below this value requires a coat. So if the temperature is below 45 degrees Fahrenheit, you need a coat. Okay, but we're going to test this two different ways. We're first going to use an or condition, and then we're going to use the and condition. Okay, so for the or condition, what we're saying is that if the wind speed is greater than 25 or the temperature is less than 45, you need a code. For the and condition, we're going to say that the temperature has to be less than 45 and the wind speed has to be greater than 25. Okay? And the conditions are pretty much, I hope, what you would expect at this point. You can see what we're doing here. We're setting for the or condition. We're setting it right here. We're checking. Obviously, we're reading the temperature and the wind speed from the user. And then we've got temperature less than the temperature for the code. That's one of the expressions. And then we've got the or, wind speed is greater than the wind speed for a code. So if it's an or, that means that if this is true, the whole thing is true. And if this is true, the whole thing is true. So either piece is true. Down here, we're using an and. So for this where code to become true, both these pieces must be true. So the temperature must be colder than the temperature for a code, and the wind speed must be greater than the wind speed for a code. Okay, so let's run this, and we'll get two output statements. Okay, so let's say that the temperature is 30 degrees Fahrenheit. That's pretty cold. And the wind speed is 60 miles per hour. It's almost a hurricane. Both cases say you need to wear a coat. So in this case, the or case says true. Obviously, both those pieces are true, and the and case would obviously say true as well. Okay, let's run another example here. Let's say that in this case, the temperature is pretty cold, but the wind speed is not so bad. So in this case, according to the first rule, which is the or rule, I need a coat because it's cold. The second rule says I don't need a coat because the wind speed in this case is too low. Okay, so hopefully that makes sense. You can see how powerful this can be. Just a really simple switch of a condition can totally change the logic, really depending on what we want. Remember, check those edge cases. Those are the ones where people tend to make mistakes on. Greater than and equal to. Sometimes you don't mean equal to, you just mean greater than, or the other way around. So testing is so important. In this video, we'll learn about C++'s compound assignment operators. These operators are very easy to use and commonly used in C++ code. The syntax for the operators is pretty simple. It's the operator you wish to use immediately followed by an equal sign. There are quite a few of these operators, but we'll focus on the mathematical operators. The bottom half of this table includes the operators that are used to manipulate bits. They're called bitwise operators, and I'll cover them later in this course. So let's look at the first one in the table, the plus equal operator. We apply the operator as in the example column. For example, left-hand side plus equals right-hand side. The meaning of this would be to increment the left-hand side by the right-hand side and then store the resulting value in the left-hand side. We'll see a few real code examples in the next slide. All of these operators work the same way. For example, the multiplication equal operator multiplies the left-hand side by the right-hand side and stores the product back in the left-hand side. Let's see some examples. Here we see some examples of using several of the compound assignment operators. Let's look at the first example, a plus equals 1. This means increment the left-hand side by the right-hand side and store the result back into the left-hand side. So this is the same as a equals a plus 1. And it's another way of incrementing a variable by 1. The second example works exactly the same way, except that we'll be dividing the a by 5, then storing the result back into a. The third example shows how the entire right-hand side is evaluated before the operator is applied. In this case, we have a multiplication equal b plus c. This means multiply a by the sum of b plus c. Then store the product back in a. In the last example, we're incrementing cost by the product of item and tax. The best tip I can give you when you write these operators is to think of the right-hand side as being inside parentheses, and you'll always have it right. In this video, we'll learn about operator precedence and associativity in C++. C++ has well-defined operator precedence and associativity rules. Here's the table showing the precedence and associativity of some of C++'s operators. Note that this table is not complete. It only shows a subset of C++'s operators. You can find complete operator precedence tables online and in most C++ books. Note that there's two columns. The first column shows the operator. The operators on higher rows have higher precedence than operators on lower rows. So as you can see, the assignment operators are down at the bottom, as you would expect, and the parenthesis operator is at the top. Operators on the same row have the same precedence. So for example, you can see that addition and subtraction have the same precedence. I think precedence is pretty easy to understand. We learned operator precedence when we learned math in grammar school. It's the same idea here, except we have more operators to consider. The second column is the associativity column. This is the part that many times confuses students and even C++ programmers. Notice that associativity is left to right or right to left. Let's see what it means. So what's associativity all about? Suppose you have an expression with two adjacent operators and these operators are different, like we see in the first example. We can look for operators in the precedence chart, and if one of the operators has higher precedence than the other, then that's the operator that's applied first. This is exactly like we've been doing with our math that we've learned. But suppose the two operators are the same or they're different, but they have the same level of precedence. Now precedence doesn't really help us. In this case, we determine how the operators are applied by using their associativity. In the second example, we have the same operator, op1, used adjacently. If op1 associates left to right, then we apply the operator to expression 1 and expression 2 first. If op1 associates right to left, then we apply the operator to expression 2 and expression 3 first. Of course, you can always use parentheses to remove any doubt and be sure that your result is what you expect. Using parentheses is good practice with complex expressions. Let's see a couple of simple examples. In the first example, we have three operators: the assignment operator, the addition operator, and the multiplication operator. The precedence chart tells us that the multiplication operator has the highest precedence, followed by addition, followed by assignment. So I've rewritten the same statement on line 2, showing the order of evaluation by including parentheses. Note that the evaluation takes place in order of multiplication, addition, and finally assignment. In the second example, we again have three operators: the assignment operator, the addition operator, and the subtraction operator. In this case, addition and subtraction are of higher precedence than assignment, but they both have the same precedence. So in this case, we need to use their associativity to determine the order of evaluation. We see that plus and minus associate left to right. I've rewritten this example using parentheses to show the order of evaluation. Many beginning C++ programmers keep an operator precedence chart handy when they first start out with C++. After not too long, you get to know the operators, and this becomes second nature, just like using math precedence did the more we used it in school. Welcome to the Section 8 challenge. For this program, I'm going to be using US dollars and cents, but feel free to use whatever currency system you're familiar with or you want to use. The idea here is you want to write a program that asks the user to enter the following. Ask them to enter an integer representing the number of cents. You can assume that the number of cents entered is greater than or equal to 0. The program then displays how to provide that change to the user. So in the US, we have $1 is 100 cents, a quarter is 25 cents, a dime is 10 cents, a nickel is 5 cents, and a penny is 1 cent. So in this example, suppose the user enters 92 cents. Your results will display that you can provide this change as follows: no dollars, 3 quarters, that would be 75 cents, a dime, which would be another 10 cents, that would give you 85, the nickel is 5, there's your 90, and the 2 pennies, there's your 92. As I said, feel free to use your own currency system. Also, think of how you might want to solve this problem using the modulo operator. When I give you my solution, I'll have two solutions. I'll have one without the modulo operator and one that uses the modulo operator, just so you can see two different ways to approach the problem. Quick hint, please don't just sit down and start coding this. Think about how you want to solve it. Write down some pseudocode, that's English-like statements, so you can get your thoughts straight. Figure out what your algorithm is or your steps that you want to use to solve the program. So have fun, make sure you test your program. Don't forget to test 0, Don't forget to test large numbers. And what I'm going to do is I'm going to do a couple of sample runs just so you can see how this works. So in this example, it says enter an amount in cents. So let's say I type in 92 cents. And the program responds, you can provide change for this as follows. $0, 3/4, 1 dime, 1 nickel, 2 pennies. Just like we would expect. As I mentioned, don't forget to test with 0. And we should get all zeros straight down the line. And let's say we want to test this with 267 cents. That's $2.67. In this case, we've got our $2. We've got 2 quarters. That gives us 50. The dime gives us 60. The nickel, 65. And the 2 pennies, 67. So there are your 267 cents. All right, so have a go at it. And when you come back, go to the solution section and I'll go over my solution. Good luck. Okay, so welcome to the Section 8 Challenge Solution. I hope you were able to solve this problem, and I hope it was fun to do. And I hope you tested it and tweaked it, made it your own, added some features to it, and so forth. Let me just go through a couple of solutions. First, we'll do the solution without using the modulo operator. So I'm going to scroll up here, and let me just explain what I've got going on. Here's my main right at the beginning. Okay, so I've defined conversion constants. These are just simple integers, and it's the value in cents of $1, a quarter, a dime, and a nickel. Okay, so $1 is 100 cents, a quarter is 25 cents, and so forth. Then I've got another integer called change amount. This is what I'm asking the user to enter. All right, so let's suppose that we're entering 92 here, and we'll walk through a simple example. Here I'm declaring all the variables that I'm going to need. Dollars, quarters, dimes, nickels, and pennies are going to contain the number of dollars, quarters, dimes, nickels, and pennies that I need to provide the change. And then I'm going to have another variable called balance, and that's going to be a balance, a running balance. So every time that I figure out I need $2, and I'm going to subtract $2 from the original amount until I get down to 0. Okay, so that's my my algorithm, or my solution is basically to determine how much of the highest currency I need, and then subtract that and have a running balance until it becomes 0. All right, so let's do this example here. And I'm just going to write some letters over here. I'll write dollars, quarters, dimes, nickels, and pennies, so we can keep it running. And I'll have a balance variable here as well. All right, so let's start. We're right about here on line 57. And we need to figure out how many dollars are in 92 cents. Well, there are none, right? So what we want to do is we want to divide the change amount, which in this case is 92, divide that by the dollar value, which is 100 cents per dollar. In this case, that's going to give me a 0. Remember, we're using integer division here, so I'm going to get to 0, which says no dollars. Makes sense, right? Because I've got less than 100 cents. Now I need to update my balance. Well, how do I do that? I decrement however many dollars times 100. Well, I had 0 here, right? So in this case, the change amount is going to be 92. And I'm going to subtract from that 0 times 100. Okay, so in this case, I'm not subtracting anything. My balance becomes 92. Okay, so that's the first step. Now we need to determine how many quarters we need. So I'm going to take that balance, which is 92, and I'm going to divide it by the quarters value, which is 25 cents. And that will give me a 3, right? 75 cents. So I need 3 quarters. Now what I want to do is I want to subtract that 75 cents from the 92. And in this case, I'm using a compound operator right here, the minus equals. So all I'm saying is balance equals balance minus the right-hand side. Well, the right-hand side is 3 quarters times 25 cents each, which is the 75. Okay, so I'm going to subtract 75 from the balance, which is going to give me 17. So that's my current balance. Now I can work on the dimes. How many dimes? Well, it's the balance, which is 17 divided by 10 cents per dime. So this is going to give me 1. So that's 1 dime. And I'm going to do the same thing here. Hopefully you can see what's going on. I'm going to subtract 1 dime, which is 10 cents each, from the balance. So I'm going to subtract 10 from the balance. Gives me 7. Now I'm going to figure out how many nickels I need. 7 divided by 5 cents per nickel. So I need 1 nickel. I subtract 5 from the 7, and I end up with 2. My balance is the number of pennies I need. I don't need to do any more calculations. And that gives me the 2 pennies. And we're basically done. So if we add up all of this, let's test this out. This is going to give me 0. This is going to give me 25 times 3, which is 75 cents. This will give me the 75. This will give me 10. 1 times 10, 1 times 5, and 2 times 1. If I add all those guys up, I should have 75, 85, 92. Exactly what I expected. Okay, so that gives you an example of one way to approach this. We'll do it really quickly with another example here. Let's say we wanted to use something like 267. So let me clear this, and I'll go through this one really quickly this time. So let's say it's 267 is the amount that the user entered. Okay, so here, how many dollars? Well, 267 divided by 100, right? 100 cents per dollar. That's going to give me $2. Then what I want to do is I want to subtract, I'll run my balance up here, those 200, which gives me 67 cents. That's my balance. How many quarters in 67 cents? Divide that by 25. That gives me 2 quarters, which is 50 cents. I'm subtracting 50 cents, and we're right back to where we were with the other problem where we've got 17. How many dimes? Divide that by 10. It gives me 1 dime. That's 10 cents. I subtract 10 from that. I end up with 7. How many nickels? Divide that by 5. It gives me the 1 nickel. And I've got 2 left, which is my pennies. Right? So this gives us, right here, 100 times 2. It gives us the 200. This gives me 50. This gives me 10, 5, and 2. Add all that up. I get 250, 260, 270. I'm sorry, 200, 250, 267, which is exactly what we started out with. Okay, now we can take advantage of something here. If you notice, if I have 267 and I divide that by 100, let's say, that gives me $2, integer division. But notice that I have a remainder. My remainder is 67, right? That's where we can use the modulo operator to rework this a little bit. So we'll do that next. Okay, so let's look at another solution. This time we'll be using the modulo operator. So suppose the user enters 267 for the change amount. And I've put all these on the same file. That way you can play around with both of them a lot easier. So in this case, I'm zeroing everything out, just like when we started. So I've got 267 cents is what the user's entered. And we'll just keep a running total over here for the dollars, the quarters, the dimes, the nickels, and the pennies. Okay, so how many dollars? Well, we divide 267 by 100 cents per dollar, and that gives us the $2. So we definitely need that. Now, rather than subtract the 2 times 100 from the 267 as we did before, we can take advantage of the modulo operator. So in this case, the change amount is 267 mod 100. Right? This gives us 2 with a remainder of 67. So the effect is exactly like subtracting 200 from 267. Okay? So what we can do is we'll keep our balance down here this time just to have a little bit more room. In this case, our balance is going to be 67. That's what we just assigned right here. Okay. Now, let's figure out how many quarters we have. Well, our balance is 67. Divide that by 25 cents per quarter, and that gives us 2 quarters. So now again, instead of subtracting 50 from 67, we could just use the modulo operator. Here I'm using the compound operator. So it's balance equals balance mod quarter value. Same idea. So balance is 67 mod 25 gives us 2 quarters, right? That's 50 with a remainder of 17. So our balance becomes 17. And then from this point forward, I think you could see what's happening. Our balance is now 17 divided by 10 cents per dime gives us 1 dime. And then we do the same modulo operator. So we're going to have 17 mod 10 gives us 1 with a remainder of 7. That's really what we care about, is the remainder in this case. How many nickels? 7 divided by 5 cents per nickel. It gives us 1 nickel. And then we do the mod operator one last time. We're going to say the balance would be 7, which is my balance, mod 5, which gives me a 1 with a remainder of 2. At that point, our balance is 2, which is the number of pennies that are left. And again, if we add this up, we're going to have $2 here, which is 200. We've got 50 cents here, 10 cents here, 5 cents here, and 2 cents here, which gives us 200, 250, 267. Okay. Another approach, to me, this approach, I'll clear this so it's not so cluttered real quick. To me, this approach, as I read it, looks easier to follow than the other approach, but they're both really doing the same thing. It's just a matter of preference and documentation. So that's it. I hope these two solutions were pretty close to yours. In this section of the course, we'll go over the control structures that allow you to control the flow of execution in your program. So far, you've learned how to write programs that run sequentially, that is, one statement followed by another and so forth. You can solve many problems using sequence, but now is when we really take advantage of the power of programming. In this section, we'll go over the selection and iteration control structures in C++. Selection control structures allow you to make decisions and execute parts of your program only when certain conditions are true or false. This is so powerful and opens up a world of programming power. After we learn about the selection constructs, we'll learn about the iteration control structures. These are the constructs that let us loop and repeat parts of our program. So we have these three basic programming building blocks: sequence, selection, and iteration. With sequence, selection, and iteration, we can implement any algorithm. Let me repeat that. With sequence, selection, and iteration, we can implement any algorithm. That's amazing. Let's see some of the C++ selection statements. The main selection powerhouse in most programming languages is the if statement. If a condition is true, then you do something. We can also add the failing condition to an if statement and get the if-else statement. In this case, if a condition is true, you do something, and if the condition is false, you do something else. So you're basically making a simple binary decision. We can also nest if statements one inside the other. For example, if my favorite football team is playing today, then if the game is on now, then record it. Sometimes if statements get pretty long and complex, so C++ has a switch statement that has some benefits when we're comparing integer-based discrete elements. Finally, C++ has a really neat operator called the conditional operator that's basically an if-else statement wrapped up in an operator. We'll go over all of these selection control flow constructs in detail. Then we'll look at the iteration or looping constructs. C++ has three basic looping constructs: the for loop, the while loop, and the do while loop. There's also a range-based for loop that's great to use with ranges of items and collections of items like arrays and vectors. We can control how many times we loop in many ways. The continue and break statements allow us to reloop and break out of loops whenever we want. Finally, we'll talk about the infinite loop. That's a loop that loops forever. Well, at least until we break out of it. And nested loops. These are loops within loops that are great for working with multi-dimensional structures like two-dimensional arrays or vectors. Everything you've learned up to this point will now be used with these control structures: variable declarations, assignment, testing for equality, relational and logical operators, and more. Let's get started and learn these powerful constructs.